Hello there, and welcome to Life Beyond Seen, where curiosity settles in beside you and science takes its time, never hurrying, never raising its voice, simply wandering with you through the questions that tug at the edges of the world. Tonight we're travelling somewhere far quieter than most places people talk about. It isn't a distant star or a hidden galaxy or the ruins of an ancient city. It's something much closer, something tucked deep beneath our own oceans, a place that almost feels like it's trying to stay forgotten. You and I are going to take a slow look at why we can't truly explore Galathea Deep, that remote trough in the Western Pacific where the water weighs more than mountains and the light has never once managed to reach the bottom. It's a part of Earth that remains almost completely out of reach, not because we lack curiosity, but because the planet itself has drawn a boundary we still struggle to cross. Before we descend toward that distant trench, I'd love to know where you're listening from tonight. Maybe you're close to the sea, maybe far from it. Maybe it's early morning where you are, or late evening, or one of those quiet hours when most people sleep and the world feels a little softer. Wherever you are in your own part of the day, thank you for spending a bit of that time here. And if you find this kind of gentle company helpful, or if these slow stories help settle your mind after a long stretch of busyness, a like or a subscription would mean a lot. It helps this quiet space reach people who might need a slower pace, a calmer voice, or simply a moment that isn't rushing them anywhere. Now take a moment, let your shoulders relax, adjust your breathing to something comfortable, and ease into the story ahead. Because exploring the deepest places on Earth isn't something done with sudden jumps or sharp angles. It takes a gradual drift, the way sediment falls through water grain by grain, always moving but never rushing. And Galathea Deep, hidden inside the Mariana Trench, asks for that kind of steady approach. Even the scientists who study it speak of it with a kind of careful patience, as if acknowledging that the place itself sets the rules long before any research vessel or submersible arrives. The first thing to understand is that Galathea Deep isn't simply a hole in the ocean floor. It's a narrow, twisting scar carved by tectonic plates, pressed down by a force that never lets up. The Pacific Plate sinks beneath the Philippine Plate here, dragging the seafloor downward into a chasm so extreme that calling it deep barely captures the reality. If Mount Everest were placed inside it, the summit would still sit far below the surface, and even that doesn't fully express what makes this place different from every shallower part of the ocean. The descent itself is more like entering an entirely separate world. With every few dozen meters of depth, familiar rules change. Light disappears long before you're even close to the bottom. Pressure rises to levels that don't just crush objects, they restructure the materials those objects are made from. Temperatures drift toward freezing. Currents slow into sluggish movements that seem almost too weak to have force. But they still carry enough momentum to complicate anything humans try to send down. People sometimes imagine the deep ocean the way it appears in drawings and documentaries, as if submarines glide smoothly through wide open space. But the truth is more complicated. Most of the world beneath a few hundred meters is pitch black, with no sound but the hum of your own equipment and no landmarks to guide you. You're surrounded by water so dense with pressure that anything not built perfectly will be flattened in an instant. Galathea Deep is the most unforgiving version of this environment. You can't see it directly. You can only infer its presence from measurements, sensors, and the rare glimpses we've managed to capture. Even then, those glimpses are more like fragments than portraits. Grainy footage, scattered readings, and brief descents that end long before anyone could truly examine the place in detail. You might wonder why, after all the advances in technology, after all the satellites and probes and rovers we've sent to the edges of space, we still struggle to reach a part of our own ocean. The answer begins with the simple fact that exploring the deep sea requires working inside the planet rather than above it. Space is empty and vast, but it doesn't crush you. The deep ocean is dense and unrelenting, pressing inward from every side. Even the strongest spacecraft wouldn't last seconds under that kind of force. so every attempt to travel downward demands materials and engineering that push right up against the limits of what's possible. And still, the ocean tends to win. Try to imagine a small research capsule descending into that darkness. It leaves the surface, passes through the first layers where sunlight still diffuses, then enters the region where everything begins to dim. Soon there's no light at all. The pressure doubles, triples, multiplies again and again. The walls of the vessel creak even if they were built to withstand thousands of atmospheric units. Instruments strain. Temperature gauges settle close to freezing. Communication systems grow weaker as the water column above becomes thicker and thicker. And this is all happening while the vessel is still nowhere near the depth we're talking about. Galathea Deep sits at around 10,540 metres down, depending on the survey you follow. That's so far beneath the surface that every single piece of machinery must operate flawlessly. A tiny failure can be catastrophic, and there is no margin for error in a place that remote. Even the act of getting there demands hours of careful descent. In that time, anything can happen. A current might shift unexpectedly, a tether might twist, a misreading might cause a piece of equipment to drift off course, and once something is lost at that depth, it's almost impossible to retrieve. Another challenge is that the deep ocean, especially in this trench, is shaped by pressure-driven chemistry that doesn't match conditions anywhere else. Water here behaves differently. It's denser, less forgiving, and able to infiltrate even microscopic imperfections in a vessel's hull. If it finds one, even a flaw too small for a human eye to detect, the force of the surrounding environment can expand it instantly. A crack becomes a fracture becomes a structural collapse. It sounds dramatic, but it's simply how physics works at this scale. Nature doesn't hesitate. For scientists who attempt to work here, the task involves more than simply designing a strong vessel. They must build systems capable of functioning under conditions that strain electronics, motors, lights, cameras and sensors. Normal batteries behave unpredictably. Standard wiring becomes unreliable. Lubricants thicken or freeze. Metals contract. Plastics become brittle. Even the best machines must be filled with special fluids and engineered with unconventional geometries just to survive. And for all that care, the lifespan of a deep-sea probe in a trench environment is usually short. People sometimes assume that if we can build machines that survive space, we can build machines that survive anything. But space and the deep ocean present opposite extremes. In space, the difficulty is emptiness. In the deepest ocean, the difficulty is pressure. Pressure is far harder to resist. Space tries to pull things apart. The deep sea tries to crush them inward from every direction. Even the strongest structure eventually buckles unless it's shaped exactly right. Spheres tend to survive best. Anything with flat surfaces, angles, or flexible joints becomes a weakness. And research equipment needs all sorts of shapes and parts, so compromises are always made. There's also the fact that the trench isn't a simple vertical pit. It has ridges, slopes, side valleys, and unpredictable terrain. Sending a vessel down is one thing. Navigating once you get there is another. A few submersibles have reached similar depths, but they rarely stay long, and they rarely explore widely. They mostly descend, touch the bottom, capture footage or samples, and return before the risk increases. To truly explore Galathea Deep, we would need machines capable of moving across the seafloor reliably, transmitting data through a barrier of crushing water, and surviving long enough to map the environment. We're not quite there yet. Even communication is difficult. Radio waves don't travel well underwater, especially not at extreme depths. Any signal weakens almost immediately, so researchers must rely on acoustics, basically sound waves, to relay information. But sound travels slowly and can be distorted by water density, temperature and terrain. It's like trying to hold a conversation in a building with thousands of walls, each reflecting your voice in strange ways. Sometimes signals reach the surface clearly, other times they vanish or become scrambled. You might send instructions and wait several seconds for confirmation. only to discover that the equipment misunderstood or didn't receive them at all. All of this makes Galathea Deep feel less like a place and more like a threshold, a point where human tools begin to falter, where the environment itself insists on control. You might think that with enough determination, enough funding and enough innovation, we'll eventually unlock its secrets fully. And maybe we will someday. But at the moment, the trench remains a region that resists being known in detail. We glimpse pieces of it, small fragments of video or sensor data, hints of creatures that live under conditions we would never survive. But the full portrait remains out of reach. There's something humbling about that, something grounding. In a world where technology seems capable of revealing almost anything, here is a part of our own planet that refuses to yield easily. It reminds us that the Earth still has places beyond the limits of our experience, places that can't be hurried, places where progress moves slowly, cautiously, quietly. And that's where our descent begins, with the understanding that exploring Galathea Deep isn't just a matter of curiosity. It's a confrontation with the limits of human engineering, biology, and endurance. As we move forward, we'll look more closely at why this part of the ocean remains one of the least accessible places on the planet, and what exactly stands in the way each time we try to go farther, stay longer, or learn more about the world hidden below. When you think about the oceans, it's easy to imagine vast stretches of blue stretching from horizon to horizon, waves folding over one another, the familiar surface where ships travel and weather forms. But everything we usually picture exists in only the thinnest portion of what the ocean actually is. Beneath that thin layer is a descending series of environments that grow steadily stranger the farther down you go, until you reach depths where the conditions are so unusual that even our best tools struggle to function. Galathea Deep sits within this realm, far beyond what most people think of as deep water, in a zone that remains almost entirely untouched, despite decades of attempts to understand it. To understand why we barely access this place, it helps to start with how little of the ocean we've seen at all. People sometimes say we've explored more of the moon than the deep sea, and while that line gets repeated often, it isn't far off. Satellites can map the moon in detail, but they can't map the ocean floor clearly through kilometres of dense water. Sonar gives us outlines, but not precision. Most of the ocean floor has never been directly observed. It's simply too deep, too dark, too difficult to reach. And Galathea Deep falls into the category of places we know exist because of measurements, not because we've spent much time there. It's a location marked mostly by numbers on charts, not by long recordings or extended surveys. Most research involving this part of the Mariana system is done from far above it. Ships pass overhead, dragging sensors or dropping weighted instruments that sink down and gather limited data before the pressure forces them to return. These are brief interactions, not extended visits. Each attempt yields a few readings, maybe a sample or two, sometimes a photograph, but nothing close to the kind of detailed information we gather near the surface. The deeper the equipment goes, the shorter the window of time it can operate. Batteries drain quickly in cold water, cables become strained by weight and tension. Every second in that environment brings new stress on the machinery. People sometimes ask why we don't simply build stronger equipment and send it down for longer, as if adding a bit more metal or increasing the thickness of the hull would solve the problem. But the deeper you go, the more pressure builds, and it does so in a way that scales quickly. By the time you reach several thousand meters, the force pressing inward on every square inch is comparable to stacking a small mountain on top of whatever you've sent down. Nothing about that is simple. Every design choice becomes a negotiation between weight, durability, cost, and function. Build something strong enough to survive and it becomes too heavy to maneuver. Lighten it and it fails before reaching the bottom. That's why so much of our understanding of the deep sea comes from single dives that last a few hours at most. A submersible drops down, touches the sea floor, collects a few images, perhaps a bit of sediment, then heads back up before the risks become unacceptable. Imagine trying to map an entire continent by landing there for 10 minutes at a time, always in a different spot, always rushing to leave before something breaks. That's essentially where we stand when it comes to Galathea Deep. We gather pieces and hope they fit together, but the gaps between those bits of information are enormous. Another problem is that the deeper parts of the trench aren't open and flat. They're shaped by shifting plates, landslides, and geological movement. The terrain isn't smooth or predictable. Slopes drop off suddenly, ridges rise unexpectedly, crevices run across the seafloor like deep cuts. So even when a submersible survives the pressure and makes it down, it still has to navigate a landscape that is more complicated than anything on the surface. If you picture a wide valley or a spacious underwater plain, that's not what these depths look like. They're more like narrow, twisting corridors or steeply angled walls with little room to maneuver. Cameras can only see a short distance in total darkness, so every movement must be slow and deliberate. One wrong turn could wedge the vessel against a rock face, and you can't just step outside to push it free. To make matters worse, most trenches have fine sediment resting on the bottom that gets stirred up easily. The slightest movement from a thruster can send clouds of particles swirling upward, completely blocking visibility. This means that even if a submersible reaches the bottom, its own movements can blind it. Imagine trying to explore a cave with a floodlight, and every step kicks up dust until you can't see more than a few centimeters. That's what underwater navigation at these depths can feel like. Sometimes the best recordings taken at the bottom of the trench show nothing but hazy darkness, with occasional specks drifting past the lens. Even the act of descending introduces challenges that limit what we learn. A dive to these depths takes several hours. The ascent takes just as long. Most submersibles can only operate for a limited duration before batteries deplete or life support needs to be conserved. So the window for actual observation is incredibly small. You spend most of the mission going up or down, not exploring. That makes every moment count, but also means there's little time for detailed study. If something unexpected happens, like a technical issue or a sudden shift in current, the dive must end early. There is no sense of luxury down here. The environment dictates the schedule. You might think that autonomous vehicles could help solve this problem by removing the need for humans to be inside the machine, and to some degree they do help. Autonomous vehicles can stay longer and take more risks, but they still face the same pressure and terrain issues as any crewed vessel. And the deeper they go, the more communication becomes a problem. It's easy to lose track of an autonomous probe in deep water. Signals don't travel well, GPS doesn't work, and once a machine goes silent at that depth, there's almost no way to find it. Many early attempts at deep-sea automation ended this way. Researchers would send down a device, wait for it to return, and eventually conclude that it never would. Somewhere in the darkness, the machine failed silently, leaving no trace of where or how. This uncertainty makes it hard to justify sending down expensive equipment unless the chances of success are extremely high. There's also the issue of biological hazards, though not in the dramatic sense. There are no giant sea creatures crushing submersibles or mysterious forces dragging machines away. But the deep sea has life adapted to conditions that would break most materials. Some organisms produce corrosive chemicals, others attach themselves to surfaces in ways that can interfere with delicate sensors. Microbes thrive on metals, wiring, and insulation. Even at these depths, bacteria can damage equipment faster than expected. It's one thing to design a hull that resists pressure. It's another to design one that survives both pressure and the unique micro-ecosystems of the deep. Then there is the question of cost. A single deep-diving submersible might represent years of funding. Every mission costs thousands per hour, and because of the risks involved, missions must be planned with extreme caution. Weather on the surface must be perfect. Sea conditions must be predictable. The crew must be experienced. Support ships must be equipped with specialized cranes, winches, sensors, and emergency measures. Coordinating all of this is complex, expensive, and time-consuming. So even if the technology exists, opportunities to use it are limited. And because we rarely get to visit these depths, Every trip begins with a certain degree of uncertainty. Conditions change. Geological activity reshapes the landscape. Sediment slides alter the slope of the walls. A path that was clear on one dive might be blocked on the next. This means that long-term study is almost impossible. There's no guarantee that an instrument placed on the seafloor will still be accessible months later. Sometimes devices get buried, toppled, or dragged away by subtle underwater movement. Despite all of this, researchers continue to try. They send down new probes, refine designs, test materials, and push boundaries bit by bit. But progress is slow. The deep sea rewards patience more than ambition. If space exploration is like sprinting into open air, deep sea exploration is like crawling inch by inch through a dark and narrow tunnel while feeling the walls press in. We've learned a great deal from the few glimpses we've managed, but those glimpses form only a fraction of a much larger picture. What makes this all the more striking is that some creatures thrive in the very environment that challenges our best equipment. They endure pressure that would flatten titanium structures. They move across the seafloor with ease. They feed, reproduce, and navigate without light. Their bodies contain biochemical adaptations we still struggle to replicate. Watching them through the lens of a submersible's camera is a reminder that life isn't limited by the same thresholds we are. Yet even they are difficult to study because they appear only briefly in our recordings, sometimes drifting past without hesitation, as if unaware that they live in one of the harshest environments on Earth. These observations often raise more questions than answers. We see organisms that shouldn't be able to withstand such conditions, sediments that shift in ways we don't fully understand, geological formations that seem to defy expectations, and while each new finding is valuable, it also underscores how much remains unknown. The more we learn, the clearer it becomes that Galathea Deep sits beyond the regions we can easily investigate. It is part of the Earth, yet feels far removed from the rest of our experience. This is why we barely touch the abyss at all, not because we lack interest, but because every attempt to reach it confronts us with the limits of what our tools can handle. The trench offers no shortcuts, no gentle routes, no forgiving margins. It demands precision, durability, patience, and resources, all in overwhelming amounts, and even then, it gives back only fragments. As we continue downward into the story, the challenges become more specific and more extreme, shaping every effort we make to understand what lies in the most remote parts of the ocean. Our next step brings us face to face with the force that defines these depths more than anything else. The force that reduces the strongest materials to fragile structures if they're not built exactly right. When people imagine the bottom of the ocean, they often think of darkness first. Then maybe cold or quiet or strange creatures drifting past a faint beam of light. But if you talk to the engineers, researchers, and physicists who spend their careers studying the deepest places on Earth, they talk about something else entirely. They talk about pressure. Not the kind you feel on a long flight when your ears pop, not the ache you get when you dive a few meters underwater, but a force so immense that it becomes almost impossible to imagine. A force that squeezes inward from every direction, constantly, relentlessly, without even the slightest break. A force that never tires, never weakens, and never negotiates. And in Galathea Deep, this force becomes the single biggest barrier between us, and a full understanding of what lies there. To get a sense of what this pressure actually means, it helps to start with the simple idea that water is heavy. A single cubic meter of it weighs about a metric ton. That sounds manageable until you try to picture what happens when that weight stacks upward for more than 10,000 meters. Every additional layer of water adds weight to the layers below it. Multiply this over and over, 1,000 times, 2,000 times, 5,000 times, until you reach the trench. By that point, the pressure is beyond anything you naturally encounter on the surface. It reaches more than 1,000 times the pressure at sea level. That number might sit neatly on a page. But the real experience of it is difficult to translate because nothing in everyday life prepares us for such an environment. If you placed a car at the bottom of Galathea Deep, it wouldn't simply dent or buckle. It would collapse inward instantly, crushed from all sides. The air inside it would be forced into a tiny fraction of its former volume. The materials wouldn't just bend, they would fail. Glass would shatter before reaching a fraction of that depth. Steel beams that look unbreakable on land would fold like thin foil. Even thick metal plates carefully shaped and reinforced show signs of strain long before they reach the trench. You might assume that the solution is simply to build stronger structures, thicker walls, more reinforcement. But that's not how deep-sea engineering works. Strength alone isn't enough. The shape of a vessel becomes just as important as the material. Flat surfaces are weaknesses because pressure doesn't distribute evenly across them. Corners become focal points for stress. Even small imperfections, too small to see without specialized equipment, can become catastrophic when the pressure multiplies them. A microscopic flaw in a weld, a tiny bubble in metal, a slight misalignment of a joint, any of these can cause a sudden failure. And failure at these depths isn't slow, it's instant. This is why vessels built to withstand extreme depths are almost always spherical. A sphere distributes pressure evenly. That's the only shape that actually works in a predictable way when water presses inward from every direction. But a sphere isn't practical for many of the tasks scientists want to perform. Most equipment requires arms, sensors, lights, thrusters, cameras, sampling devices and cables. The moment you attach anything that sticks out, you create a potential point of collapse. So engineers face a constant balancing act. The safer the shape, the less useful the equipment becomes. The more useful the equipment, the more fragile the structure becomes. Galathea Deep pushes this trade-off to its limits. There have been a handful of vessels capable of reaching similar depths, but even those that succeed do so with intense caution and significant limitations. The famous dives to the Mariana Trench, including the ones carried out by research institutions and private explorers, required years of planning and testing to ensure that every weld, every bolt, every seal was strong enough. And even then, the dives lasted only hours. No one stays at that depth long, not because of fear, but because every minute adds cumulative risk to a structure that cannot afford even the tiniest weakness. Even the materials we trust most struggle here. Steel becomes vulnerable. Titanium can withstand impressive loads, but must be machined with extraordinary precision. Composite materials show promise, but they behave unpredictably at high pressure. Ceramics can resist crushing forces but crack without warning. Every option comes with a drawback that becomes magnified by the environment. Researchers sometimes describe the pressure in another way. Imagine holding a small object in your hand. At the surface, you feel nothing unusual. Now picture the same object 10,000 meters down, where the pressure tops 1,000 atmospheres. For every square centimeter of its surface, the water is pressing with hundreds of kilograms of force. Spread that across the entire surface of a vessel, and the numbers become staggering. If the structure isn't perfect, the water finds the weak point, and once it does, the collapse is total. Even electronics, which might seem immune to crushing forces, aren't spared. Pressure forces water molecules into any space they can reach. If a seal isn't absolutely flawless, water seeps in, even through points that look airtight. Once moisture reaches sensitive components, the equipment shorts out almost immediately. Batteries distort under pressure. Light fixtures implode. Fiber optic cables collapse. Even if the core hull survives, the systems that make exploration possible often fail long before reaching the deepest point. This is part of why we've only collected limited footage of the trench. Cameras struggle at these depths. LED arrays must be encased in pressure-resistant housings, and even then the risk of failure is significant. When one of these housings collapses, it doesn't just crack, it bursts inward with incredible force, sending shards and fragments into surrounding components. A single implosion can take out an entire set of instruments, ending a mission instantly. It becomes more complicated when you consider movement. A stationary sphere can resist pressure better than a moving vessel, but exploring the seafloor requires motion. Thrusters must push the vessel forward or backward. Those thrusters need openings where water can move through. Every opening is a compromise. Every compromise is a potential failure point. And unlike in shallow water, you can't simply turn around and surface if something seems off. A malfunction at depth can trap a vessel for hours during the ascent, leaving it vulnerable the entire time. The internal environment of the vessel also becomes a design challenge. Humans require breathable air at standard pressure. Machines require heat regulation, power supplies, and stable electronics. To maintain this internal environment, the vessel must withstand not only external pressure, but internal pressure differences. A tiny leak can cause pressure to rise rapidly inside the hull. Even a small crack can turn into a dangerous rupture. The deeper you go, the more these risks multiply. This is why most trenches, including Galathea Deep, remain out of reach for direct human exploration. Only a handful of crude dives to the deepest regions of the ocean have ever succeeded, and each one carried enormous risk. That's why scientists increasingly rely on remotely operated vehicles and autonomous probes. But even these unmanned machines face restrictions. When pressure damages a human-occupied submersible, it's a life-threatening emergency. When pressure destroys a robotic probe, it's still a major loss, both financially and scientifically. And because these probes are expensive and difficult to build, very few are made. Losing one represents years of work and large amounts of funding. The deeper parts of the ocean also create pressure gradients that change quickly. A minor shift of a few meters can expose equipment to dramatically different forces. This means every descent must be controlled with precision. A sudden drop or collision with a ridge could push a vessel into regions where it no longer meets the safety threshold. That unpredictability is part of why the trench feels so remote, even though it sits on our own planet. Another aspect often overlooked is that pressure affects not only the hull, but every liquid and gas inside the vessel. Oils used to lubricate motors behave differently. They become thicker, sometimes nearly solid. Hydraulic fluids compress. Air bubbles trapped inside lines create dangerous inconsistencies. Pressure-resistant oils have been developed, but they come with trade-offs. Some reduce efficiency, others break down over time. Every system must be tested repeatedly to ensure it doesn't seize up or behave unexpectedly when the vessel reaches deeper levels. Cables and connectors pose their own challenges. Water pressure squeezes cable insulation, making it brittle. Connectors can warp, plugs can loosen. A single compromised cable can cut off communication or power. Many deep-sea failures occur because of small problems like these rather than catastrophic hull collapse. A light stops working, a sensor stops reporting, a motor sticks. Over time, enough small problems accumulate, and the mission must end early. Pressure also affects sampling tools. Grippers must function in cold, dense water without bending or cracking. If a claw manages to pick up a rock or biological sample, the sample itself might behave differently under pressure. Some organisms die or change shape before they can be studied. Sediments can compact differently. Gases trapped inside materials may escape before the sample returns to the surface. So even when a probe survives the dive, the data it gathers may still be incomplete. All of these factors come together to create an environment where pressure dominates every moment, every design choice, every attempt to gather knowledge. Nothing operates normally. Everything must be designed specifically for these depths. And even then, success is never guaranteed. Yet despite all this difficulty, the extreme pressure at Galathea Deep isn't just a challenge. It's a defining characteristic of the environment. The creatures that live there have evolved under these conditions. Their bodies are shaped by pressure, literally and chemically. Their proteins, membranes, and structures adapt in ways human-made materials cannot easily replicate. These organisms show that life can thrive in conditions we find impossible. But to understand them fully, we would need to study them in situ rather than bringing them to the surface. And studying them in situ means sending instruments that can survive long enough to observe without failing. That remains a major limitation. Pressure also influences geological processes. Rocks behave differently under extreme loads. They deform, shift, and grind in ways that surface rocks do not. The trench walls may release small sediments constantly, creating underwater avalanches or slides. These movements can damage equipment or bury sensors. Under pressure, even small geological events create significant effects. All of this makes pressure the primary reason we cannot simply visit Galathea deep whenever we want. It sets a firm boundary. It tells us what is possible and what is not. And while technology continues to improve, the environment remains the same. It doesn't adjust for our convenience. It doesn't make exceptions. It waits, steady and immense, unchanged by whether a probe arrives or not. This force shapes everything we attempt in the deep. It dictates how we design vessels, how we plan missions, how we prepare for failures, and how we interpret the data that comes back. It is the invisible presence that defines the entire experience of deep exploration. Without considering pressure, nothing at these depths makes sense. With pressure in mind, everything becomes clearer, even if it remains difficult. And as we continue drifting deeper into the reasons Galathea Deep stays beyond our reach, pressure becomes only one part of a larger collection of constraints. Another obstacle awaits in the form of an environment that lacks something humans rely on completely, something that disappears long before we even approach the trench and changes how every instrument, camera, and human eye functions. When people talk about the deep ocean being dark, the word itself almost feels too small for what actually waits down there. Darkness at the surface is temporary. It shifts with sunsets and cloud cover and the flicker of artificial lights. Even on the blackest night, our eyes adjust. There are streetlights, screens, reflections on windows, lamps glowing in distant buildings, stars overhead. There's always something, even if it's faint. But once you begin descending through the ocean, the light disappears in a way that doesn't feel gradual. It feels absolute. And by the time you reach the depth where Galathea Deep exists, darkness isn't just the absence of light. It's the default condition of everything. It's been that way for longer than sunlight has reached the surface of the Earth, longer than most forms of life have existed at all. It's a kind of darkness that isn't defined by what you can or can't see, but by the way every form of biological, mechanical and sensory perception is changed by the simple fact that nothing with eyes can rely on them there. If you drop beneath the first few 100 meters, the world dims quickly. The colours of the surface fade one by one. Reds go first, then oranges, then yellows, leaving everything washed in shades of green and blue. Keep sinking, and even that faint palette disappears. Soon, there's no colour at all because there's no light to reveal it. The transition feels abrupt to anyone who has made deep dives. One moment you can see the faint shimmer of a downward beam. The next, you're inside a void that gives you no visual information whatsoever, and that's still nowhere near the depth we're talking about. Sunlight fades completely around 1,000 meters down. Past that point, the ocean exists in perpetual night. But even this isn't the kind of night people imagine when they hear the word. Human darkness always contains the possibility of light. Someone can flip a switch or strike a match. The sky will brighten in a matter of hours. Underwater darkness at the depth of Galathea Deep is permanent. No star, moon, or surface lamp can penetrate it. No reflection reaches it. No natural glow from the surface trickles down. Nothing arrives except what the trench itself produces, and that is almost nothing at all. This creates immediate problems for exploration because, unlike many forms of life adapted to these depths, our tools require optical information. Cameras rely on light to form images. Lasers and beams reflect only if they hit surfaces. Even sonar, which uses sound instead of vision, becomes less reliable when the environment is unpredictable. or the terrain reflects signals in ways that confuse the instruments. Darkness strips us of one of our primary investigative senses, and the deeper you go, the more every task becomes a challenge of feeling through the environment rather than seeing it. Researchers who've been involved in deep-sea missions often describe the experience of watching a live feed from a submersible as almost disorienting. The camera views show a narrow window of space illuminated only by the lights mounted on the vessel. Everything outside that cone of light remains completely invisible. You cannot tell if there's a wall a meter away or a cliff edge dropping off below you. You cannot see obstacles, currents, or creatures unless they pass directly into the small region lit by the vessel's lamps, and those lamps only reveal part of what they're pointed at. Particles suspended in the water scatter the beams, creating a hazy field that obscures distant details. The farther you try to see, the more the light gets swallowed. This makes navigation extremely slow. A submersible might crawl forward at a pace so cautious, it barely seems to move at all. The pilot watches for shadows, movement, or hints of texture. But in a place like Galathea Deep, even shadows are unreliable, because the absence of light means the only shadows that exist are the ones your own equipment creates. The darkness doesn't give shape to anything. The machines have to provide every bit of illumination themselves, and that light barely makes it far enough to give useful context. People sometimes assume that the deep sea is filled with glowing animals, and it's true that many creatures produce bioluminescence. But bioluminescent light doesn't spread widely. It's meant for communication, hunting, camouflage, distraction, and survival. It flickers, pulses, or shines in small bursts. It rarely provides broad illumination. In some cases, animals use light to lure prey or signal mates, but you won't find anything down there that lights up the environment the way headlights reveal a road. So even though life has found its own way of dealing with the absence of sunlight, it doesn't solve the problems we face when we try to explore. Galathea Deep sits far below the main layers of bioluminescent activity. The creatures that live there tend to produce weaker light or none at all. Many rely on touch, chemical signals, or slow drifting movements that require little sensory interpretation. They evolved in a world where vision wasn't necessary because visibility was never available to them. Eyes are rare, transparent tissues are common, bodies build themselves around the knowledge that sight would provide no advantage. In that kind of environment, our technology must work against a world that doesn't want to be seen. Lights must be incredibly bright to illuminate even a small patch of ground. But bright lights attract animals that can be confused, stressed, or harmed by artificial illumination. They also heat local water slightly, which draws in fast-moving particles that block the lens. Some missions keep the lights dim to avoid environmental disruption, but dim lights create poor visibility. Others use high-intensity beams, but these beams can dazzle sensors or reflect off sediment in ways that distort the image. There's no perfect solution. Darkness also creates challenges for mapping. At shallower depths, scientists can use cameras, lasers, and multi-angle imaging to build three-dimensional reconstructions of terrain. But in the deepest regions, those methods fail. You cannot map what you cannot see. Sonar mapping helps, but it lacks the detail needed to navigate complex geological structures. A sonar map might show a slope, but not the cracks or overhangs that could trap a submersible. It might reveal a general outline of the trench, but not the ridges and depressions that shape the environment. So while we can create broad models of Galathea Deep, we lack detailed maps of its floor. And because of the darkness, every mission relies heavily on artificial lighting systems that themselves must withstand pressure, cold, and chemical exposure. A cracked light housing means total visual loss. If one lamp fails, the pilot must rely on the remaining lights, and that creates uneven illumination. If all lights fail, the dive is effectively over. The vessel must return to the surface without completing its intended tasks. A dive that lasts 12 hours could end after only a few minutes of data collection, all because a single light fixture was compromised. This dependence on illumination means that darkness on its own becomes an environmental hazard. Even if the vessel survives pressure, cold, currents, and technical complications, it can still lose its ability to navigate simply because the surrounding world offers no feedback unless the lamps reveal it. And the lamps cannot reveal enough. People often wonder why we don't use more powerful lights. The reason is simple. In water, light doesn't travel the way it does in air. It loses strength fast. Water absorbs, scatters, and diffuses. A lighthouse beam might travel kilometres through air, but only a few metres through deep seawater, especially when particles are floating everywhere. Turning up the brightness doesn't increase visibility much. It just increases glare. It creates bright spots in the foreground and nothing in the distance. Darkness also affects how video and photographs are interpreted. Small particles look like floating debris but could be living organisms. Shadows look like shapes, but might be illusions caused by uneven lighting. This makes every recording harder to analyse. Scientists sometimes spend months studying a few minutes of footage because they must account for every possibility. Did a moving shape represent a creature or drifting sediment? Was a strange pattern on the seafloor a geological feature or simply the distortion caused by shifting light? Without natural illumination, you cannot cross-reference anything. Even the simplest tasks like recognizing a slope or identifying a rock formation become more complicated when visual cues don't behave normally. A pilot might think they see a vertical wall, only to realize later that the wall was actually a shadow cast onto a flat surface. Depth perception becomes unreliable. Judging distances becomes guesswork. That's part of why diving into the trench must be done slowly and carefully. For scientists observing the feed from a deep camera, the darkness can be mentally fatiguing. Watching a small area of illuminated water for hours, waiting for brief glimpses of life or geology, means processing limited visual information constantly. Your eyes search for contrast, but the only contrast comes from the narrow cone of light. Everything outside that cone might as well not exist. It creates a sense of isolation because the environment gives no visual context. There are no horizons, no sense of direction, nothing to anchor the mind. Imagine trying to understand a forest by shining a flashlight in pitch-black night, but never seeing more than a few feet around you. You could spend weeks doing this and still know almost nothing about the forest as a whole. That's the scale of the problem scientists face when working in the trench. Without sunlight, without reflection, without any form of natural illumination, every discovery is made through a keyhole. This darkness also affects time perception. Pilots and researchers often lose track of how long they've been watching the footage. With no changes in lighting to mark the passage of time, with no shifts in shadow or brightness, the environment appears the same second after second. It gives dives a slow, almost suspended feeling. And while that calm might sound pleasant, it actually places significant strain on concentration. A sudden movement or unexpected shape can feel startling because so little usually changes in the field of view, and the trench itself offers no clues. On land, darkness hides familiar shapes. Underwater darkness hides everything entirely. The trench could be opening wider or narrowing. The floor could be rising or falling. The vessel could be near a cliff edge without any indication. Pilots must trust their instruments far more than their eyes, and even instruments can behave unpredictably near large geological structures. Magnetic anomalies, sudden shifts in the terrain, and unusual water chemistry can all affect readings in small but important ways. This absence of light shapes the lives of the creatures that inhabit the trench as well. Many of them have no eyes or only rudimentary ones. Their senses rely on pressure waves, chemical gradients, or energy detection. The darkness is not a challenge for them. It's the environment they evolved into. Their bodies do not waste energy building vision systems they can't use. Their entire biology is designed around a world where sight contributes nothing. For these organisms, darkness is not an obstacle. It's simply reality. For us, it's a barrier that limits everything we attempt. We're creatures built to use vision as our primary sense. Remove that, and our entire approach to exploration must change. The darkness at Galathea Deep may not crush metal or distort electronics in the way pressure does, but it still defines what is possible. It narrows the field of observation, imposes restrictions on navigation, disrupts perception, and complicates data collection. It ensures that each dive reveals only a tiny fraction of the environment. That's why even after years of exploration, the trench remains largely unknown. The lack of light means that most of what exists there has never been seen by any camera or sensor we've used. And as we move onward, there is another element waiting that makes the experience at these depths even more challenging. Something subtle at first, but powerful in its own way. While darkness removes light, the cold removes heat so effectively that every machine, every chemical reaction, every biological process slows down unless it is specifically engineered to cope. If darkness removes the ability to see in the deep ocean, then cold removes the ability for almost anything to behave the way it does in the world we're familiar with. At first glance, cold might seem simple. People deal with low temperatures all the time. They walk outside in winter, open a freezer door, or watch frost forming on windows. But the cold found at the depth of Galathea Deep belongs to a different scale. One that doesn't simply make things uncomfortable or slow. It changes the behaviour of materials, affects the speed of chemical reactions, alters how machines function, and pushes biological limits into forms that seem almost disconnected from normal metabolism. The temperature down there hovers just above freezing, but the environment is so stable and so extreme that the cold becomes just as defining as the pressure and darkness around it. In the deep ocean, the water temperature remains close to 2 or 3 degrees Celsius. It can vary slightly depending on location, but in the deepest trenches the values remain nearly constant. There are no warm currents drifting through, no sunlight warming the surface above, no seasonal shifts to create variation. The cold persists every hour, every day, every year. Because the temperature is so uniform and unchanging, anything that adapts to this environment must adapt completely. There is no break from it. No pocket of warmer water to retreat into, no surge of heat to offset the losses. The cold dictates the structure of life and the behaviour of matter. Exploration equipment suffers in these conditions long before reaching the trench floor. Metals contract in cold water. Polymeric materials stiffen. Lubricants thicken until they slow moving parts or freeze them entirely. Electrical systems generate their own heat during operation, but that heat dissipates immediately into the surrounding water. The cold pulls it away faster than the systems can produce it. For many devices, temperature regulation becomes a constant challenge. A battery warming itself to function normally must fight against the surrounding water siphoning heat away at remarkable speed. And when a battery gets too cold, its chemical processes slow down. Voltage drops. Power output decreases. If it becomes cold enough, the battery can fail completely or provide only a fraction of its intended performance. This is one reason why deep diving vehicles must carry far more power than they actually need during operation. A significant percentage of that energy goes toward maintaining internal temperatures. If the inside of a machine drops too low, processors slow, instruments malfunction, and sensors lose accuracy. It isn't because the electronics break permanently, but because their normal functions depend on predictable operating temperatures. Cold removes that predictability. Engineers must insulate, heat, and manage these components continuously, or the machine becomes unreliable. Some scientific tools simply cannot operate when the temperature drops beyond a certain threshold. Hydrophones become less sensitive. Chemical sensors slow until they take minutes to register a change that should take seconds. Cameras fog internally when small temperature deviations affect moisture inside their housings. Even specialized cables can become rigid, losing flexibility and risking fractures when they must bend or turn. The cold turns every small weakness into a more noticeable problem, and when combined with the crushing pressure, Even the tiniest defect becomes a source of potential failure. Another lesser-known challenge is the way cold affects time-based processes. Chemical reactions that occur quickly at room temperature can take far longer here. Biological metabolism slows down dramatically. This means that everything from decomposition to nutrient cycling to the growth rate of organisms moves at a pace that feels almost suspended. Scientists sometimes refer to deep-sea ecosystems as slow ecosystems, not because life rarely changes, but because every process takes longer. Food webs move sluggishly. Organic matter sinks through the water column at an unhurried drift. When something dies on the surface and sinks toward the trench, it can take months or years to reach the bottom. Once there, its decomposition is slower than expected. The cold also impacts how fluids behave inside machines. Hydraulic systems rely on fluid movement to create motion, but fluid viscosity increases dramatically in cold environments. That means every pump, valve and piston must work harder to perform basic tasks. If a robotic arm needs to extend or rotate, the machinery must overcome resistance created by the thickened fluid. If engineers use thinner fluids to compensate, those fluids may become unstable or compressible at high pressures. If they use thicker fluids, the cold makes them almost solid. There's a narrow window of workable options, and finding the right balance for the trench is a painstaking process. Biological life faces similar limitations. Enzymes function within specific temperature ranges. Too much cold slows their activity so much that metabolism barely moves forward. That's why many organisms that live in extreme depths have evolved enzymes that function efficiently at low temperatures. These enzymes remain flexible and reactive, even when the surrounding water is cold enough to slow most molecular interactions. But those adaptations come with trade-offs. The same enzymes might break down if exposed to warmer temperatures at the surface. That means if scientists bring these creatures up too quickly, or without maintaining their environmental conditions, the organisms can die before being studied. Their bodies are so specialized for the cold that they cannot survive even brief exposure to temperatures we consider normal. This is why studying deep-sea organisms is far more complicated than simply retrieving them. They must be brought up with extreme care. Pressures must be matched gradually or maintained. Temperatures must be controlled precisely. If either variable shifts too fast, cells rupture, proteins denature, and the organism becomes damaged. This sensitivity makes it difficult to understand how these creatures function in their natural environment. It's not that they are fragile in the trench. Quite the opposite. They thrive there. The problem is that the cold environment they require is hostile to our equipment. Cold also makes the water itself behave differently. Its density increases, its movement slows. Currents at these depths are steady but not strong. They don't mix or swirl the way surface currents do. They move in slow, creeping flows that can carry fine particles a long distance over time without ever seeming forceful. This affects how sediment accumulates. Sediment settles slowly and evenly, creating soft layers that can shift under the weight of a submersible, or collapse when disturbed by a thruster. Cold water holds less thermal energy, so small disturbances dissipate quickly. That means any motion, whether natural or caused by a machine, has long-lasting effects because the environment cannot redistribute heat in meaningful ways. The cold also impacts sound. Sound travels differently depending on temperature, pressure, and salinity. At the depth of Galathea Deep, sound can bend, reflect, or distort in ways that complicate communication with submersibles. Even small temperature differences can alter the path of an acoustic signal. This adds another layer of difficulty to an already challenging task. If researchers cannot communicate with their machines reliably, they cannot control them properly. And if they cannot control them, they risk losing them to the environment. Every piece of equipment used in this region needs careful material selection. Metals that maintain strength in warmth might become brittle in cold. Plastics that remain flexible at the surface can crack when chilled. Adhesives weaken, sealants shrink. Even the rubber used for insulation or structural dampening becomes stiff. Many failures in deep-sea expeditions occur not because of pressure alone, but because of the combined effect of pressure and cold. A part weakened by low temperature becomes more vulnerable to compression. A seal pulled tight by pressure becomes more rigid in cold. The combination pushes systems to their limits. Another interesting consequence of constant cold is that it affects how long missions can last. Batteries drain faster in cold water, which reduces operational time. Heating systems must run continuously, drawing more energy. Cameras and lights generate a small amount of heat, but not enough to counteract the surrounding environment. Over long missions, heat loss accumulates. The longer a submersible stays at depth, the more cold infiltrates the machine. Eventually, the equipment must return to the surface simply because the internal temperature is becoming too low for safe operation. Even the descent itself exposes the vessel gradually to colder conditions. At various depths, temperature profiles change slightly. Certain layers have slightly warmer or cooler pockets. The machine must adjust continuously. Sensors must be calibrated to new conditions. Software systems need to interpret readings that shift subtly as the environment changes. The deeper the machine goes, the more stable the temperature becomes, but stability at that level doesn't simplify the problem. It only means the cold remains constant rather than fluctuating. Humans who enter these environments inside crewed vessels rely on the insulation and heating systems within the pressurized cabin to maintain comfortable conditions. But the structure around them endures the full brunt of the cold. Even if the people inside feel warm, the outer layers of the vessel experience intense temperature differences. These differences stress materials, especially at points where different metals meet. One metal might contract faster than another, creating gaps or tension in joints. Engineers must plan for these differences by choosing materials that expand and contract at similar rates. But even the best planning cannot remove every potential point of stress. Cold also affects the fine details of data collection. Chemical sensors might detect trace elements differently at low temperatures. Pressure sensors must adjust for temperature-related density changes in the water. Instruments designed to measure biological activity must account for slower metabolic rates. Recording devices must function in conditions that interfere with their internal processes. The cold doesn't break these systems directly, but it slows them, complicates them, and adds layers of interpretation that scientists must consider. And yet, the creatures living in Galathea Deep handle these temperatures without difficulty. Their cells contain high concentrations of compounds that maintain fluidity at low temperatures. Their membranes remain flexible. Their proteins remain active. Their internal chemistry operates at a pace suited perfectly for the environment. They do not fight the cold, they evolve into it. That adaptation fascinates researchers because it shows that life can thrive in what seems like an inhospitable world. But studying those adaptations closely is limited by the same cold that shapes them. Machines cannot observe the trench for long periods without losing function. And organisms brought to the surface lose the conditions they require. This means much of what we know about deep-sea biology comes from brief glimpses or indirect methods. True, sustained observation within the trench would require equipment capable of withstanding cold, pressure, and darkness for months or years at a time, something we have not yet achieved. Even if we built such a device, retrieving it without damage or data loss would be a challenge. The cold at this depth ensures that every system must work harder than intended. All of these factors illustrate how cold isn't merely a temperature reading on a chart. It shapes the pace of life, the design of machines, the behavior of materials, and the strategy of exploration. It slows processes in a way that makes everything more deliberate. Time feels stretched, not in the psychological sense, but in the physical sense. Reactions that would take seconds elsewhere take longer here. The environment doesn't hurry. It doesn't encourage movement or rapid change. It settles into its own rhythm, and anything entering it must adapt to that pace or risk failure. As we continue through the reasons we can't fully explore Galathea deep, the cold becomes just one part of a larger chain of barriers that exist in layers. One of those layers involves the water itself, not simply as a massive liquid, but as a stratified system with boundaries that resist mixing, movement, and exploration. The deeper we go into this story, the more the ocean reveals that the difficulties don't come from one factor alone. They come from a network of conditions that reinforce one another and create a world we can observe only in small pieces. The deeper you go into the ocean, the more it stops behaving like a single body of water. It becomes a collection of layers, each with its own rules. These layers don't blend the way people expect. They stack, resist, and separate, almost like invisible walls that make the descent into places like Galathea Deep even more complicated than the cold, darkness, and pressure already suggest. And while those earlier conditions set the overall tone of the environment, the layered nature of the ocean acts as a series of gates that slow, distort, or interfere with anything that tries to pass through them. When you drop a stone into a lake, it sinks straight down. The water above it behaves predictably. But in the open ocean, especially in the deep Pacific, water isn't uniform. Temperature, salinity, density, chemistry, and even the movement of internal waves all create boundaries that hold their shape for years or even decades. These aren't boundaries you can see. They don't look like lines or walls, but machines detect them immediately. Submersibles shift slightly when they cross one. Sensors record changes in temperature or salinity. Sonar pings bounce differently. Tethers strain. Lights pick up tiny particles drifting differently on either side. Every layer has its own fingerprint, and when you're working with technologies that rely on stability, those fingerprints matter. The first major layer encountered during descent is the thermocline, a zone where temperature drops rapidly over a relatively short depth range. This sudden shift affects buoyancy, signal transmission, and the movement of currents. A submersible moving steadily downward might suddenly slow or drift sideways when crossing the thermocline, not because anything malfunctioned, but because the density of the water changed. Engineers have to calibrate for this change so the vessel doesn't misinterpret the shift as a mechanical problem. Above the thermocline, water can still hold traces of sunlight, heat from the surface, and mixing from wind and waves. Below it, the ocean becomes colder, heavier, and far less interactive with the world above. Once past that layer, machines enter a region where salinity differences begin to matter. Salt concentration affects density just as temperature does. In some regions of the deep Pacific, layers of water with slightly different salinity settle on top of one another without mixing. These layers can be stable for years. When a machine passes through them, it feels the change. Motion becomes less predictable. Thrusters must work harder or softer depending on whether the surrounding water is more or less dense. Instruments that rely on sound feel the impact as well. Sonar waves bend or slow, creating distorted readings. A pilot watching the instrument sees these changes and must interpret them quickly to avoid drifting off course. As the descent continues toward Galathea Deep, another series of layers appears. One's defined not just by temperature and salinity, but by chemical differences. Oxygen levels drop, nutrients shift, trace elements concentrate differently. Some layers contain more dissolved carbon dioxide, others contain nearly none. These variations affect more than biology. They affect corrosion, electrical conductivity, and how certain materials behave. A metal part that corrodes slowly in one layer might corrode faster in another. An electrical connection stable near the surface might misbehave when surrounded by water with different conductivity. Engineers test for these conditions extensively, but testing in a lab can only approximate the complexity found in the real trench. Some layers hold suspended particles left over from ancient sediment flows or geological activity. These particles can be microscopic, drifting so slowly that they never settle fully on the seafloor. They remain suspended within the layer, forming a sort of underwater haze. Cameras catch this haze as a soft cloud of drifting specks. Lights reflect off them. The more particles present, the harder it becomes to see anything beyond a few meters. Pilots must reduce thruster use to avoid stirring up more sediment, but reducing thruster use affects maneuverability. In a place requiring careful navigation, these trade-offs complicate everything. Beyond the average layers known to most oceanographers, the deep Pacific contains something even stranger: internal waves. These waves don't rise on the surface. They move along density boundaries deep underwater. They can be huge, rising tens or even hundreds of meters, but completely invisible from above. When a submersible crosses an internal wave, it might feel a sudden lift or drop. Sensors register changes in flow. Instruments detecting pressure or motion record fluctuations that make machine behavior less predictable. Internal waves can sweep over a tether, causing it to slacken or tighten suddenly. They can nudge a vehicle off course without any warning. And because they occur far below the reach of surface observations, predicting them is difficult. Sound moves differently in each layer, which complicates navigation further. A submersible might send a signal upward to its support ship, only to have the signal travel along a curved path instead of a straight one. This phenomenon, caused by changes in water density and temperature, means acoustic signals can be lost, delayed, or reflected. Engineers spend considerable time calculating potential distortions in sound waves so they can interpret communications correctly. Even so, unexpected variations often force the team to pause and reassess. As the descent approaches the depths near Galathea Deep, water becomes incredibly stable. Mixing between layers slows nearly to a halt. The deeper the layer, the older the water. Some of it has circulated through the ocean for centuries before reaching this point. Its composition reflects that long journey. Trace elements from distant regions accumulate in specific concentrations. Biological processes that occur at mid-depths leave chemical signatures behind. Water that enters the trench floor must follow narrow paths shaped by currents, gravity, and the structure of the trench itself, creating pockets that behave differently from the water above. One of the most significant layered barriers at the deepest levels is the Hadal boundary, the region where the deep ocean transitions into the trench environment. This boundary isn't marked by large temperature or salinity changes. Instead, it's defined by density and pressure interacting with the shape of the trench. The Hadal zone contains water that settles into steep valleys and remains there. Because the trench walls rise sharply, the water doesn't mix easily with surrounding layers. It sits like a trapped mass, slowly circulating in patterns shaped by geology rather than wind or surface conditions. Machines entering this boundary find themselves surrounded by incredibly still water, but that stillness hides slow currents that creep along the trench floor. These sluggish flows carry fine sediments that have accumulated for millennia. The sediments sit in delicate layers. A machine's arrival can disrupt them instantly. Even a gentle burst from a thruster can send sediment into the water column, creating a local cloud that obscures vision for hours. If a probe accidentally settles onto soft sediment, it might sink slightly into the layer. Not enough to become trapped permanently, but enough to make takeoff difficult. Some autonomous vehicles have been lost because particulate suspension blinded their sensors and prevented navigation. Visibility wasn't restored in time to correct the drift, and the machines eventually collided with terrain or remained lost within the trench. Layered barriers also affect how organic matter moves through the water column. Dead plankton, fish fragments, algae, and other pieces of biological debris drift downward slowly. They pass through various layers that alter how they decay, how fast they move, and what creatures consume them. In some layers, bacteria thrive and decompose the material quickly. In others, cold and oxygen scarcity slow the process dramatically. This affects food availability on the trench floor. Some organisms rely on these slow-falling particles, and their entire survival depends on predictable patterns in the layered ocean. If these layers shift, food distribution changes. For scientists trying to understand deep ecosystems, this means they must track not only the organisms on the seafloor, but also the water layers above, which act like conveyor belts for nutrients. Movement between layers isn't always smooth. Certain transitions behave almost like interfaces in a material. A machine pushing from one layer into another may tilt or sway. Pressure changes slightly. Temperature shifts by fractions of a degree that still matter at these depths. Sensors recalibrate. Pilots adjust. Every crossing becomes a task. When crossing dozens of layers on a single descent, small adjustments accumulate into significant operational challenges. Engineers designing deep-sea equipment must consider these layered barriers just as carefully as they consider pressure or cold. They build systems that adjust buoyancy automatically when entering new density layers. They design control algorithms that respond smoothly to sudden shifts in movement. They calibrate acoustic systems to account for sound bending differently in each layer. And still, many dives encounter unexpected complications because the layers change over time. Conditions measured on one expedition rarely match those found years later. They shift subtly due to seasonal cycles, tectonic activity, or larger-scale ocean circulation. These changes make planning uncertain. One of the most difficult layers to navigate is the acoustic shadow zone, a region where sound waves refract away from the submersible. If the machine enters this layer, communication with the support vessel becomes unreliable or fails entirely. Engineers must reroute signals, increase power, or reposition the vessel to regain contact. But repositioning takes time, and time is limited on deep dives. Every minute of miscommunication reduces the amount of useful observation possible. And even once the submersible passes through all these layers, the trench itself contains internal boundaries that aren't related to temperature or salinity. These boundaries form when water trapped in the trench behaves differently from the water just above it. The trench's shape funnels movement into narrow pathways, guiding water through slopes, ridges, and depressions in slow, predictable patterns. But many of these patterns remain poorly understood. They shift with seismic activity. They change after landslides. They respond to long-term geological forces. A machine entering one of these internal patterns might drift sideways inexplicably, or feel resistance where none existed before. These internal boundaries complicate sampling as well. If a robot extends an arm to collect sediment or biological material, water movement can push the sample away. If the sample is successfully collected, the water surrounding it may change its temperature or chemical composition before the machine reaches the surface. Scientists must interpret the data knowing that the layered environment influences everything, even after collection. Despite all this complexity, these ocean layers aren't obstacles created to hinder exploration. They're simply the natural structure of Earth's largest environment. Millions of years of currents, climate patterns, biological processes, and geological shifts have shaped the ocean into a tiered system. Creatures living at each layer evolve to match the conditions of that particular environment. Some layers host enormous populations of small organisms adapted to low-light conditions. Others contain bacteria that process chemical compounds drifting down from above. The trench layers host creatures that thrive on slow metabolic rates and limited resources. Each part supports the next, forming a network of connections that science is still trying to map. For those attempting to explore Galathea deep, these layers act as both challenges and clues. They reveal the complexity of the system, but also make it difficult to reach the bottom with equipment intact. Even if pressure, darkness, and cold were manageable, these layered barriers would still demand specialized tools and detailed planning. A mission ignoring them wouldn't make it far. And while these layers complicate descent, they also affect how we retrieve information. A probe rising back to the surface must pass through the same barriers in reverse. Conditions shift again. Sensors recalibrate. Pressure drops. Temperature rises. Data logs adjust. Even the samples collected change slightly as they move through each layer. Scientists must account for these transitions when examining the results of a dive. The layered structure of the ocean becomes part of the story told by every data point, As we continue downward into the reasons why Galathea Deep remains so difficult to explore, it becomes clear that each barrier reinforces the next. Pressure makes equipment fragile. Darkness makes navigation uncertain. Cold slows processes. Layered water creates unpredictability. And beyond these challenges lies another barrier that complicates deep exploration even further: the limitations of the machines themselves. Even at their best, they struggle to survive in a world built around conditions far outside the range of human experience. The deeper we go into the reasons Galathea Deep resists exploration, the more obvious it becomes that even our best machines struggle long before they ever touch the seafloor. Many people imagine deep ocean expeditions as a matter of lowering a submersible, watching it sink, and waiting for it to send back images or samples. In reality, the process is fragile at every step, and most failures happen during the descent rather than the actual investigation on the bottom. The environment doesn't wait to test a vehicle when it reaches the trench. It begins testing it almost immediately. Every dive toward the deepest parts of the ocean starts with preparation on the deck of a ship. Engineers inspect every seal, every connection, every sensor, every battery casing, every panel, every bolt. They do this because they know that even a small flaw can turn into a large problem at depth. A tiny crack in an acrylic dome might seem harmless on the surface, but becomes a point of collapse thousands of meters down. A cable that looks secure in the sunlight might shift when it cools. An instrument that functioned perfectly in the lab can behave unpredictably in cold salt water. Engineers must predict these problems early because once the vehicle leaves the ship, the time to correct anything has already passed. Even before a vessel is placed in the water, the deck itself becomes a testing ground. Equipment must survive vibration from the ship's engines, movement from waves, and the constant shifting of weight as the vessel is prepared. Delicate instruments are jostled, electronics are exposed to salty air, hinges stiffen. The team works quickly but carefully, knowing that the environment they are standing in isn't benign either. The ocean begins affecting the mission long before descent begins. Once the vehicle enters the water, it must pass through all the layers described earlier. Each layer adds a complication the machine wasn't dealing with on deck. The thermocline alters buoyancy. Changed salinity affects how the vehicle sinks. Internal waves nudge it sideways. Suspension particles cloud sensors. The vehicle tries to remain stable, but stability in an ocean column is always relative. There is no firm ground or open air to rely on. Movement is constant, even when it seems still. At shallow depths, sensors usually behave well. Cameras work. Acoustic signals travel clearly. Thrusters respond normally. But as the machine sinks, electronics begin cooling. Batteries release energy more slowly. Motors become less efficient. Even the insulation meant to protect sensitive components gradually loses warmth. The water outside remains barely above freezing, and the cold moves inward through the hull, creeping steadily towards systems that depend on stable temperatures. During this period, the support team watches a constant stream of data. They monitor power levels, internal temperature readings, navigation systems, external pressure sensors, camera feeds, and instrument diagnostics. The descent isn't a time of waiting, it's a time of active observation. The vehicle is vulnerable, and the team must detect signs of trouble early. A pressure gauge might spike unexpectedly. A thruster might draw more current than it should. A sensor might begin drifting out of calibration. If the team sees something concerning, they may need to reverse the dive immediately because continuing could lead to a failure that strands the machine permanently. Pressure increases steadily, and every increase puts strain on the hull, the joints, the cables, and any protruding instruments. Even though the materials were chosen specifically for their strength, pressure reveals weaknesses no test chamber can fully simulate. Real ocean pressure doesn't rise perfectly smoothly. It shifts depending on temperature, density, and the layered structure of the water. A probe passing through one region might suddenly feel a slightly increased load. In many cases, the change is barely noticeable. But when building for extreme environments, even small differences matter. One of the most common failure points for deep-sea equipment is the housing for batteries and electronics. These housings must withstand pressure while keeping internal components in a dry, stable environment. If even a hairline fracture forms, water forces its way inside almost instantly. A few drops are enough to shut down a circuit board. A small leak becomes catastrophic quickly because water doesn't seep at depth. It is driven inward with enormous force. There have been missions where engineers watched helplessly as a probe's internal temperature sensor suddenly matched the ocean temperature, indicating that the hull had been compromised and the interior was flooding. Once water reaches critical components, the machine is lost. Lighting systems fail frequently. A lamp housing might crack under pressure. The bulb inside might shatter. LED arrays might distort under temperature stress. When lights fail, cameras become useless. Many dives have been cut short simply because a single light malfunctioned halfway down the descent. Turning back is the only safe option, because continuing blind increases the risk of collision with unseen terrain. Even with infrared or low-light systems, deep-sea exploration depends heavily on artificial illumination, and illumination is only as reliable as the housing built for it. Thrusters represent another point of weakness. They rely on moving parts, and moving parts are trouble at extreme depths. Cold thickens lubricants. Pressure compresses seals. Motors strain. Bearings tighten. A thruster that fails at depth can cause a vehicle to drift or become unstable. In an environment where visibility is compromised and the terrain is unpredictable, drift becomes dangerous quickly. The pilot might not realize the submersible is moving sideways until the sensors detect proximity to a wall or sea floor. In some cases, the drift remains slight but persistent, forcing the pilot to overcorrect constantly. This drains power and increases the risk of human error. Another challenge arises from cables. If the submersible is tethered to the support ship, the cable must remain intact throughout the descent. But cables twist. They rub against the vessel. They flex under pressure. They contract in cold. They accumulate strain. If a tether fails, the vehicle loses communication and control instantly. Remote-operated vehicles are lost this way more often than most people realize. Even the most durable tethers can fail when exposed to thousands of meters of pressure and movement. And once a tethered machine is lost, it rarely returns. It sinks to the bottom, becoming one more piece of equipment that didn't survive the descent. Even autonomous vehicles, which rely on stored instructions rather than live control, face difficulties. Their navigation systems must function perfectly despite constant changes in pressure, temperature and salinity. A small error in an accelerometer reading, or a slight miscalculation in depth, can cause a vehicle to veer off course. Without human correction, these errors accumulate. Many autonomous vehicles have disappeared into the depths because the environment overwhelmed their navigation software. No dramatic crash or catastrophic failure was required. The vehicle simply drifted into terrain they couldn't detect in time. Pressure-resistant spheres, often used to house delicate electronics, sound like a perfect solution. But spheres require perfect symmetry. Any deviation can make them vulnerable to collapse. Manufacturing a truly perfect sphere is extremely difficult. Even minor imperfections can lead to failure under extreme pressure. Engineers test and retest them, but real ocean conditions reveal problems that controlled environments never show. Sometimes a sphere collapses silently. Sometimes it collapses violently. Either way, the mission ends immediately when it happens. As the vehicle approaches deeper layers, the water itself behaves differently. Sound travels strangely. Light behaves unpredictably. Sensors drift. The support ship may lose track of the probe's exact position. Even if the probe's depth sensors are working correctly, its horizontal position becomes uncertain. The support ship uses acoustic signals to track it, but those signals bend in unusual ways at depth. This makes plotting its location difficult. The deeper the descent, the wider the margin of error. A probe might think it's clear of a ridge when in reality it's drifting toward it. Marine snow, small particles of organic debris, causes problems in certain layers. These particles are harmless individually, but they scatter light and obscure vision. When a thruster kicks up sediment, the particles form clouds that linger. Lights reflect off them unpredictably. Cameras show only flickering white specks. Sonar can detect the sediment cloud and misinterpret it as a solid object. For the vehicle, this environment becomes a maze of uncertainty. If the machine cannot see and cannot rely on sonar, its operators have little choice but to retreat before losing control entirely. Another common equipment failure involves the connectors used to link external sensors to internal electronics. These connectors must create watertight seals while remaining accessible for maintenance, but pressure compresses seals unevenly. Cold stiffens them, salt water corrodes them. At shallow depths, these changes are manageable. At the depth of Galathea deep, they become unpredictable. A connector that worked perfectly 20 minutes earlier might suddenly fail. Engineers can only design so much redundancy before weight, cost, and complexity become prohibitive. Sometimes sensors report values that make no sense. A pressure gauge might show a sudden drop. A temperature sensor might spike. A depth reading might freeze. These abnormalities often indicate a deeper issue, such as a failing circuit board or a structural problem. When inconsistent data appears, the team must decide whether to trust it or abort the mission. In the deep sea, misinterpreting data can mean losing the vehicle. Many teams choose to abort at the first sign of confusion, knowing that hesitation leads to greater risk. Power systems fail frequently. Batteries tested extensively in controlled conditions behave differently when subjected to long periods of cold, darkness, and pressure. Battery might show full charge but deliver only a fraction of the expected power. Inconsistent output forces the vehicle into low power mode, reducing its ability to operate tools or maintain lighting. Once power begins dropping faster than expected, the mission must end quickly. Even if the equipment works perfectly during the descent, the act of reaching the bottom can expose new vulnerabilities. The seafloor of the trench isn't flat. It has slopes, ridges, and depressions. A vehicle might land unevenly, stressing one set of joints more than another. If a thruster stirs up sediment, visibility might vanish instantly. If the vehicle settles onto soft sediment, it might tilt slightly, placing additional strain on a side panel. Any misalignment affects future movement and increases the risk of collision during takeoff, and still, failure before arrival remains the most common outcome. Many deep-sea missions never make it to the bottom. The equipment malfunctions halfway down. A seal weakens, a cable twists, a battery overheats, a thruster jams, a sensor fails, a communication system drops out. Sometimes the failures aren't dramatic. Sometimes it's just a subtle mismatch in readings that forces the team to turn back. But every time this happens, it reminds researchers how narrow the window of success really is. Even when equipment reaches the bottom, staying there is another matter, but the real barrier comes before that, long before any meaningful exploration begins. A machine designed to explore must first survive the journey, and survival is far from guaranteed. As we move forward, the limitations of the machines themselves become only one part of the story. The deeper challenge lies in the creatures that live in this environment. Organisms adapted so thoroughly to these conditions that they highlight the gap between what life can accomplish naturally and what our tools can withstand. When we picture life in the deep ocean, it's easy to fall into familiar ideas shaped by the animals we see closer to the surface. Fish darting through reefs, schools glimmering under sunlight, dolphins cutting through waves, all moving in ways we understand. But every meter you descend toward Galathea Deep takes you farther from anything familiar. The darkness doesn't just remove colour. The cold doesn't just slow movement. The pressure doesn't just crush machines. Together, these conditions shape life into forms so different from what we expect that the creatures of the trench might as well belong to a different version of Earth entirely. What makes these organisms remarkable isn't simply their unusual appearance. It's the fact that they thrive in conditions where our most advanced equipment fails minutes after arrival. Their entire existence is built around problems that break our technology. While machines struggle against pressure, these animals use it as a foundation for stability. While electronics lose function in the cold, these organisms rely on cold to maintain their internal chemistry. While we try to push light into the dark with artificial beams, many trench dwellers evolved without needing light at all, and while our submersibles falter at the layered boundaries of the ocean, these creatures move through those layers as if they don't exist. It's tempting to imagine them as alien, but they're not alien to the trench. They are perfectly natural for it. We're the ones who don't belong there. One of the most common misconceptions about deep-sea creatures is that they must all look monstrous simply because they live without light. Some do appear unusual, with elongated limbs, transparent skin, or strange mouths. But many are small, delicate, and almost unnoticeable in the dark unless illuminated by a passing submersible. Their bodies aren't built to intimidate, they're built to survive. And survival down here requires a completely different set of biological strategies. The first adaptation most organisms possess is pressure tolerance. At the depth of Galathea deep, their bodies aren't filled with gas-filled cavities the way surface animals are. They don't have air pockets that would collapse. Instead, their internal chemistry uses dissolved compounds and fluid-filled chambers that behave predictably under intense pressure. Their proteins are structured differently as well. Proteins in surface life begin to fold improperly under high pressure, destroying normal function. Deep-sea proteins contain special molecular features that maintain flexibility and structure even under crushing force. These proteins don't fight the pressure. They're constructed to work inside it. Their cell membranes also behave differently. Membranes in surface organisms would become rigid in cold water, preventing essential functions from occurring. But the organisms of the trench use molecules that keep membranes fluid at low temperatures. This allows nutrients to move into cells and waste to move out. Without this adaptation, their cells would shut down. Engineers can create pressure-resistant metal alloys and temperature-resistant materials, but they cannot yet replicate the subtle, responsive adjustments of a living cell membrane. The creatures here do it effortlessly. Some organisms rely on chemicals that act almost like internal antifreeze. These compounds prevent ice crystals from forming, even when the water temperature nears freezing. Machines must fight the cold constantly, drawing on power to maintain internal warmth. But trench creatures float through the water without worry. Their temperature remains nearly identical to the surrounding water, adapted completely to the environment. They do not waste energy resisting the cold. They work with it. Even the absence of light shapes their design. Eyes require energy to maintain and provide no advantage here. Many animals lose them entirely. Others retain only simple light-detecting structures that do little more than sense faint glows from bioluminescence. For them, information comes from other senses. Some detect vibration. Others sense chemical changes in the water. Some use long, thin appendages that extend far from their bodies, feeling their surroundings instead of seeing them. These structures serve as both navigation tools and hunting sensors. They replace the vision we depend on. Many creatures in the trench produce faint light, but not for the purpose of illuminating the world. They use bioluminescence for communication, mating, or luring prey. Some produce flashes, others glow in steady pulses. A few send signals patterned in ways scientists still don't fully understand. Machines can record these pulses, but they cannot interpret their meaning. A creature passing through a submersible's beam might react with a flicker of light, not out of curiosity, but because the artificial glow interferes with its chemical signals. Disturbing the natural signalling system makes observation even harder. Then there are the gelatinous species, fragile-looking organisms that possess little structural rigidity, but survive extreme pressure because their bodies match the density of the surrounding water. They don't have to withstand pressure, their bodies transmit it instead. Machines cannot use this strategy. They require rigid structures. They need internal pressure different from the outside world. But gelatinous organisms settle comfortably into a world that would flatten us instantly. Their frailty, paradoxically, becomes strength. The snailfish found in trenches like the Mariana system are a perfect example. Their bones are minimal, their bodies soft, their tissues flexible. They live at depths so extreme that the pressure becomes a stabilizing force. Remove them from that environment and they would fall apart. Their biology depends on the world we find hostile. These fish move gracefully in the dark. Navigating terrain machines struggle to interpret even with advanced sensors. They feed on amphipods and other small creatures that drift through the trench. They breed in low-light conditions. Their entire existence is tuned to a world our technology isn't built to handle. Amphipods themselves demonstrate another adaptation. Pressure-resistant exoskeletons made from materials different from those of shallow water species. Their chemistry, especially in the structure of their shells, incorporates metals in ways that make them sturdier under pressure. Studying these shells could provide insights into new types of deep-resistant materials, but retrieving them without damage is extraordinarily difficult. Once brought to the surface, the pressure change alters their structure. Many samples crack or deform before researchers can study them. Other organisms rely on chemical interactions at the bottom of the trench. Some bacteria use the limited nutrients present in the cold sediment. Some feed on organic matter that falls slowly from the surface. Others rely on chemical gradients created by the movement of deep water against geological formations. Machines can measure these gradients only briefly because their sensors lose calibration quickly in the cold and layered conditions. The organisms, by contrast, live in perfect balance with them. Some species move so slowly that researchers aren't sure whether they are drifting or actively swimming. Their metabolism operates at a fraction of the speed of surface organisms. Because energy is scarce, their bodies conserve it in every way possible. They move with the water rather than against it. They feed rarely and grow slowly. Their lifespans might extend for decades or centuries. These long, slow rhythms make them difficult to observe because the timescale of their activity doesn't match the duration of the deep-sea dive. Machines stay for hours. These organisms live on timescales that make hours irrelevant. Predatory species that dwell in the trench evolve different strategies. Instead of chasing prey through the dark, they sense faint chemical signals or tiny vibrations. They strike only when opportunities present themselves. Machines attempting to observe these predators struggle because the presence of artificial lights, thrusters, and electronics disturbs the water around them. The predators sense these disturbances and avoid them. This means some species remain undocumented, known only from indirect signs such as marks on prey or unexplained movement picked up by sensors. The creatures know we are there long before our cameras find them. One of the most mysterious groups of trench organisms consists of extremely small, microbial communities that build mats on rocks or sediment. These communities perform chemical processes essential to the deep ocean's nutrient cycles. They process organic matter that settles over long periods, breaking it down in ways unique to their environment. Machines attempting to collect samples from these communities often disrupt the mats, destroying the structures before they can be studied. Even gentle flow from a submersible thruster can erase hours or years of microbial activity. The organisms themselves aren't fragile, but their environments are. Some organisms in the trench remain invisible to cameras entirely, not because they're too small, but because they reflect almost no light. Their bodies are so adapted to darkness that artificial light has little effect on them. They remain indistinct shapes, blending into the black water around them. Even specialized low-light cameras struggle to detect them. Their presence is often inferred from changes in water chemistry or movement recorded on sensitive equipment. What's especially fascinating is that many of these creatures developed these adaptations without ever encountering humans or machines. They evolved in isolation from everything we build. Their world has been stable for millions of years. Pressure does not change. Temperature does not change. Darkness does not change. They evolved to fit this environment so precisely that any attempt we make to observe them must interfere with their natural state. Our presence disturbs sediment, changes water flow, inserts artificial light, creates vibrations, and introduces sounds they aren't adapted to interpret. Every action we take disrupts something. This is one of the greatest challenges of deep ocean biology. The act of observing changes the conditions in which the creatures live. Machines cannot avoid altering the water around them. They can only minimize the disturbance. But the environment is so sensitive that even small adjustments ripple outward. This makes long-term observation extremely difficult. The creatures themselves pose no threat to exploration. There are no giant predators waiting in the trench, no mythical monsters guarding the depths. The barrier they create comes from the fact that they can survive where we cannot. They navigate environments our machines can barely tolerate. They function in conditions so precise that any deviation becomes dangerous for them. Our technology is too rigid, too warm, too bright, too noisy, and too fragile to study them fully. But despite how difficult it is to observe these organisms, their existence is crucial for understanding why Galathea Deep remains out of reach. They demonstrate how life adapts when given enough time. They show that the trench isn't empty or dead, it's filled with systems functioning on slow, steady timescales. Every layer of the trench supports something. Every chemical gradient feeds something. Every tiny drifting particle becomes food for something. The trench is not barren. It's active in ways we're only beginning to understand. Studying these organisms also reveals the limits of our tools. The creature's adaptations prove that the environment shapes everything that survives there. Machines built for surface conditions cannot expect to perform well in a world built around pressure, cold, and darkness. We can imitate some adaptations with engineering, but most remain out of reach. This means that even as technology advances, there will always be a gap between what organisms evolve to handle and what machines can endure. The next part of the story ties directly into these adaptations. While trench creatures move easily across the seafloor itself is not a stable platform. It shifts, bends, and changes over time. Understanding those movements helps explain why even reaching the bottom doesn't guarantee a safe or predictable environment for machines. When most people picture the bottom of the ocean, they imagine a still, quiet plain of sediment, maybe dotted with rocks or ridges, but fundamentally stable. A kind of remote desert floor where nothing shifts quickly. But the deeper you descend toward Galathea Deep, the less that image matches reality. The seafloor here is a part of a living, shifting system driven by pressures and forces that never rest. It sits at the boundary of tectonic plates that push, grind, and slide against each other in slow but constant motion. What looks calm in a photograph or video frame is actually a landscape that changes over years, months, and sometimes moments. And for any machine trying to explore this region, the moving ground beneath it becomes an unpredictable obstacle that complicates everything from landing to data collection to safe return. The trench exists because one tectonic plate is diving beneath another. This process is called subduction, and it doesn't happen smoothly. The plates don't glide past each other like polished surfaces. They catch, strain, and jerk. Over time, this creates cracks, ridges, slopes, and valleys. Even the deepest point of the trench changes slightly over long periods. It's not a fixed location carved in stone. Pressure pushes downward. Heat rises from below. Sediment drifts downward constantly. Everything contributes to a world where stability is temporary. For a submersible reaching the bottom of Galathea Deep, this means the landscape is nothing like a flat floor. It's a steep, uneven environment with loose sediment in some places and hardened rock in others. A slope may look shallow but actually be steep. A ridge may look solid but hide fragile layers of compacted material. A depression may appear safe to land in, but contains soft mud that swallows equipment. Machines built for exploration don't see the terrain the way we do. They interpret it through sonar, cameras and sensors, and those sensors only reveal part of the story. The seafloor in the trench is covered with sediment that falls from above. Some of it comes from the slow rain of organic matter drifting downward over months. Some comes from landslides triggered thousands of meters higher on the trench's upper walls. Some comes from volcanic activity deeper within the earth. Over long stretches of time, these sediments accumulate into thick layers. But the layers don't stay in place. They shift under pressure. They slide when disturbed. They move like heavy, slow-moving liquids in some conditions. This is why landing a submersible on the trench floor is risky. The landing gear sinks unexpectedly. The vehicle tilts. A thruster might blow sediment into the water column, obscuring sensors and creating a cloud that takes hours to settle. A slight tilt can shift weight onto joints that weren't designed to carry it, and if the machine is resting on unstable ground, a small tremor could cause the sediment beneath it to shift suddenly. The vehicle doesn't have legs designed for reaction. It can't brace itself. It simply rests wherever it settles. And if that resting point isn't firm, the vehicle becomes vulnerable. Many researchers compare landing on the trench floor to stepping onto deep snow with uneven ice underneath. Every point of contact can behave differently. One area might hold firm while another collapses slightly. The challenge is that submersibles don't have the sensory range to evaluate the ground beforehand. They only know how stable the ground is once they make contact. By then, if the ground is soft or shifting, the machine must compensate immediately or risk getting stuck. The movement of the seafloor isn't limited to slow sediment creep. Larger-scale geological events occur as well. Landslides can happen along the trench walls. These aren't like landslides on land where debris races downward rapidly. Underwater landslides move more slowly, but they carry enormous amounts of sediment. They release clouds of particles that drift for miles. A submersible that happens to be nearby might experience reduced visibility, unexpected currents, or difficulty maintaining depth. Even small tremors can create ripples of movement that push sediment into the water column. Seismic activity adds another layer of danger. Subduction zones are known for producing earthquakes. Most are small and go unnoticed on the surface, but even small events can create changes deep underwater. A submersible sitting quietly on the seafloor might feel a slight jolt as the plates shift. It might tilt or slide a few centimeters. These movements aren't usually catastrophic, but they increase stress on the machine. A sudden shift could also send sediment sliding down a slope. If this happens near a vehicle, it must lift off quickly to avoid being buried. But lifting off requires thrusters, and thrusters kick up more sediment, which blinds sensors and reduces control. The chain reaction makes even minor seismic activity a threat. The trench walls also contribute to instability. They rise steeply on either side of the deepest point. These walls are shaped by the grinding movement of tectonic plates. Over time, parts of the walls crack, loosen, and fall. These collapses can release chunks of rock and sediment that drop into the deeper regions. Some of this material settles gently, but some descends with enough momentum to disturb the environment significantly. Machines navigating near the walls must remain cautious. A shift in debris could block a path or create an unexpected hazard. Even without seismic activity, the seafloor moves in ways that challenge long-term observation. Sediment drifts gradually, covering instruments left behind. If scientists deploy a long-term sensor or camera, they must consider how quickly sediment will bury it. This means devices must either be elevated above the seafloor or designed to operate despite being partially buried. Both options add complexity. Elevating a device makes it more vulnerable to currents. Designing it to handle partial burial makes it more expensive and harder to build. The seafloor also hosts biological activity that affects movement. Certain organisms burrow through the sediment, creating tiny tunnels. Over time, these tunnels collapse, altering sediment structure. These small changes add up, affecting the stability of the upper layers. Machines landing on what appears to be firm ground may actually be landing on a network of voids. created by the creatures living below. The ground gives way unexpectedly. Water movement shapes the seafloor as well. Even in the deepest areas, there are slow currents that drag fine sediments across the bottom. Because the sediment particles are extremely small, they move easily. Over long periods, these flows create ripples or small dunes. They might be only a few centimetres tall, but to a machine navigating the seafloor, they matter. A vehicle travelling across these ripples must maintain balance while dealing with slight changes in elevation and texture. If the terrain is sloped, the small ripples can become channels that channel water flow in unexpected directions. That flow influences the movement of particle clouds, which affects visibility. Hydrothermal vents, although more common in mid-ocean ridges than trenches, sometimes occur near deep subduction zones. These vents release hot, mineral-rich water. While rare in Galathea Deep specifically, any vent activity nearby would affect water chemistry, sediment stability, and temperature. Machines passing close to such features must adjust quickly, and sudden shifts in water temperature can damage sensitive instruments. The combination of hot vent water and cold trench conditions creates localized regions of instability. Another subtle challenge lies in the fact that the trench floor isn't perfectly horizontal. It isn't even close. It slopes at angles that can surprise even experienced researchers. A vehicle descending vertically might approach a slope at an awkward angle. If the slope is steep, the machine risks landing unevenly. Uneven landing forces one side of the vehicle to carry more weight. This uneven distribution increases stress on joints and panels. Over hours, this can lead to fatigue. If a thruster must compensate for the tilt, it uses more energy than intended. Energy consumption increases, battery life shortens. The dive must end early. Some parts of the trench floor are covered in rocky outcrops. These formations are often jagged or uneven. Submersibles can become caught on them if they drift too close. The limited visibility means pilots often detect these obstacles late. By the time they adjust, the vehicle might be too close to avoid contact. Even a light touch can damage sensors or scratch a pressure-resistant surface in a way that affects future dives. The hardest part of dealing with a shifting sea floor is that it adds uncertainty to every decision. A pilot must consider the possibility of movement even if everything appears still. Researchers planning a mission must account for geological instability even if recent surveys show steady terrain. Engineers designing landers must include features that allow for quick liftoff if the ground becomes unstable. Each layer of planning anticipates conditions that might never occur. But the possibility is enough to justify the caution. Submersibles that use legs to land face unique challenges. The legs must distribute weight evenly across uneven ground. If one leg sinks into soft sediment, the vehicle tilts. If it tilts too far, cameras and instruments end up angled awkwardly. Thrusters must correct the tilt. But correction produces water flow that stirs sediment. Sediment reduces visibility. Reduced visibility makes correction harder. A cycle begins that stresses the machine and shortens the mission. Autonomous landers avoid the problem of piloted landings, but they face similar risks. They drop to the trench floor with minimal maneuvering. If they land on unstable ground, they may not be able to adjust. Some have tipped over, becoming useless. Others have sunk into thick sediment to the point where retrieval becomes difficult. Engineers sometimes attach flotation systems to these landers so they can rise even if partially buried. But flotation systems can fail, and even if they succeed, the rising lander can stir sediment, contaminate samples, or damage instruments. The movement of the seafloor also affects long-term deployments. A sensor placed on the bottom may shift slightly over weeks due to sediment creep. This shift affects the sensor's calibration. Data becomes less reliable. A camera positioned to observe a specific region might end up facing the wrong direction months later. A chemical sampling station might become buried. To operate in such an environment long-term, devices need to anchor themselves or adjust automatically. Anchors risk becoming stuck. Automatic adjustments require energy and complexity. The deeper the system, the more difficult these solutions become. The trench environment isn't hostile in the sense of active danger. There are no storms breaking overhead, no volcanoes erupting violently around the submersible, no predators attacking machines. But the conditions combine into a world where nothing remains static. The slow, constant movement of the seafloor becomes a quiet but persistent challenge. It creates uncertainty that cannot be measured easily, predicted reliably, or mitigated completely. What makes all of this even more challenging is that machines exploring Galathea Deep must pass through these changing conditions on limited time and limited power. Every adjustment drains energy, every correction shortens the mission. When researchers deploy equipment into a world where the ground moves beneath it, the margin for error shrinks. Even if everything else works perfectly, the seafloor itself can shorten the dive or end it entirely. And while the physical movement of the seafloor complicates exploration, the next obstacle is something less visible, but equally disruptive. It affects communication, control, and data transfer. It's the reason a submersible operating just fine at depth can still fail a mission without a single mechanical malfunction. Reaching the bottom of Galathea Deep requires surviving pressure, darkness, cold, layered barriers, and a shifting seafloor. But even if a submersible or probe manages to pass through all of these obstacles without a single mechanical failure, there is still another barrier waiting, one that cannot be welded, engineered, reinforced, or upgraded away. It isn't made of rock or water or sediment. It isn't geological, biological, or chemical. It's something far more fundamental, something that changes what exploring the trench actually means. At its core, it comes down to communication, and the reality that the deepest parts of the ocean exist in a space where our primary tools for sending and receiving information lose most of their usefulness. The moment a vehicle begins its descent from the surface, communication becomes more complicated. On land, we take connection for granted. Signals move through the air with ease. Antennas send messages across continents. Satellites relay information instantly. Underwater, none of that works the same way. Radio waves lose strength rapidly in water. Even at shallow depths, they weaken until they become unusable. At a few dozen meters, the signal breaks almost completely. By 100 meters, radio communication is gone, and Galathea Deep sits more than 10,000 meters below the surface. This means every deep ocean mission starts with an unavoidable limitation. The moment the vehicle leaves the upper layers, live communication as we understand it in everyday life disappears. The engineers aboard the support ship must rely on acoustic signals, sound waves sent through the water, to talk to the machine. These signals travel much slower than radio, they carry less information, they distort easily, and they are affected by every variable we've discussed so far. Temperature, salinity, pressure, and the presence of layers that bend or scatter sound. A single acoustic message might take several seconds to reach a submersible. The reply takes several more seconds to come back. If something goes wrong, the delay means operators must wait for confirmation at exactly the moment they want immediate response. In an environment where a few meters of drift can become dangerous, a delay of 10 or 20 seconds is significant. The deeper the vehicle goes, the more these delays grow. Sound doesn't travel in a straight line underwater. It bends downward, upward, or sideways, depending on the density of the surrounding layers. If water temperature changes slightly at one depth, the sound path curves. If salinity differs slightly at another, the path bends again. By the time the signal reaches the submersible, it might have travelled in an arc. When the sub sends its reply, the return path might follow the same arc or a different one depending on environmental shifts. This makes even the most basic communication uncertain. A short message might arrive as garbled noise. A simple instruction like a send or turn 10 degrees to port might be delayed to the point where the machine has already drifted beyond the point where that instruction makes sense. Operators must build in safety margins. They must assume communication issues will occur. They must avoid sending too many instructions in too little time, because the messages might arrive out of order or overlap. Another complication is interference. Marine life produces constant sound. Some species click, chirp, or pulse. Water movement generates noise. The ship on the surface creates vibrations. Sediment hitting the sea floor makes faint rumbles. All these noises travel through water and overlap with the acoustic frequencies used by the submersible. Engineers carefully tune the frequencies they use, selecting ones that minimize interference. But the ocean is unpredictable. A sudden shift in current might move sediment. A school of small creatures might pass through an area where sound waves are travelling. Underwater noise doesn't behave the way noise does in air. It carries farther, bends more, and fills space with overlapping waves that can mask or distort the signals the vehicle depends on. Even when the acoustic signal reaches the vehicle clearly, the amount of data it can carry is extremely small. Deep-sea communication cannot handle high-bandwidth streams. Live video is impossible. Large datasets cannot be transmitted until the machine returns to the surface. This means operators often guide the machine through still images or sparse sensor information, rather than fluid video feeds. They might get a frame every several seconds instead of continuous movement. If the camera turns to face a ridge or interesting geological feature, they see it in pieces, not as a smooth sweep. Making decisions based on fragmented data requires experience and patience. The operators must interpret what they see, while accounting for the fact that the vehicle moves slowly, the environment is unpredictable, and communication delays prevent quick adjustments. The longer a dive lasts, the more cumulative these communication challenges become. A machine operating in the trench must respond to instructions that are always slightly out of sync with the present moment. The vehicle hears the ship as it sounded seconds earlier, and the ship hears the vehicle as it was seconds earlier. No one gets a real-time picture. Everything is shifted. This isn't a problem in shallow water, where the environment changes slowly. In Galathea Deep, where sediment shifts, terrain surprises and visibility is limited, delayed decision-making becomes a serious risk. To compensate, engineers program submersibles with autonomous behaviour. If communication is lost temporarily, the vehicle switches into safe mode. It holds position or rises slowly until signal returns. In theory, this protects the machine. In practice, the environment complicates the process. Holding position in layered water is difficult. Rising through twisted sound paths means the vehicle might temporarily move into areas where communication becomes worse before it gets better. Autonomous ascent requires power. If power is low, the vehicle may not rise quickly. If it rises too slowly, currents push it off course. If it rises too quickly, it risks structural stress. Every autonomous decision involves compromise. Some expeditions use tethered vehicles to avoid these issues. A long cable connects the machine to the support ship, transmitting power and data directly. This provides stable communication, but introduces new problems. A tether thousands of meters long weighs a great deal, pulls on the vehicle constantly, and behaves unpredictably when crossing layered boundaries. It drags in currents. It vibrates in water movement. It can snag on ridges. It twists. Engineers design tethers to handle these conditions, but no tether can eliminate the risk. If it breaks, the machine loses all connection instantly. Even satellite-linked buoys cannot solve this problem, because the buoy still must transmit signals through water first. The ocean simply does not permit stable electromagnetic communication at depth. It doesn't matter how advanced the antenna is, or how strong the transmitter becomes. Water absorbs the signal, pressure distorts electronics, darkness offers no help. Cold slows reaction time, layered barriers bend the path. No antenna can change these physics. This limitation shapes the entire experience of trench exploration. When a machine moves through water, it must rely on instructions given moments earlier. When it approaches a slope, the pilot sees the slope after the machine has already begun responding to it. If a sudden drop appears in the terrain, it might take 10 or 15 seconds for the information to reach the ship, and another 10 or 15 seconds for new instructions to reach the vehicle. even with careful planning, mistakes happen. A slight misjudgment caused by communication lag can end a mission. Sometimes the communication problem isn't obvious until later. Data might appear normal on the way down, only for the team to realise during ascent that some of the depth readings were inconsistent because a sound path bent unexpectedly. Or a coordinate might be off by a few dozen metres, altering the entire interpretation of a sample's origin. These small errors accumulate. Scientists must analyse mission data carefully, correcting for the known communication limitations. This is one reason why knowledge of Galathea Deep expands slowly. Even if a machine performs perfectly mechanically, communication restricts how much can be done in the limited time available at depth. Operators must allocate time for handling communication delays, position corrections, and navigation adjustments. By the time these challenges are managed, little time remains for detailed observation. Communication problems also affect retrieval. When it's time for the vehicle to return to the surface, the ascent plan must be communicated clearly and interpreted correctly. If the acoustic connection weakens, a critical instruction may not reach the vehicle. In that case, the machine must follow pre-programmed behaviour. It might ascend automatically after a set period. But if the operator needs it to rise sooner or faster, the inability to relay that instruction becomes an operational risk. Surfacing in the wrong spot can be dangerous due to waves, currents, or nearby hazards. And because the vehicle cannot carry enough energy for complex fail-safe decisions, lost communication means fewer options. The problem grows even more complex when the mission involves multiple vehicles. If two submersibles or landers operate in the same region, their acoustic systems can interfere with one another. Signals overlap, frequency bands collide. Engineers attempt to coordinate frequencies carefully, but the underwater environment bends and spreads sound waves unpredictably. One vehicle might hear another signal faintly and interpret it as noise, or worse, interpret it as part of its own command sequence. This makes coordinated missions rare. Most expeditions use a single deep diving system at a time. This slows data collection. It restricts simultaneous observations. It limits the number of experiments that can be performed. While satellites can observe entire continents at once, deep-sea observation remains focused on tiny sections of seafloor, explored slowly by a single machine struggling against the silence imposed by the surrounding water. Communication problems also limit emergency response. If something goes wrong inside the vehicle, if pressure causes a partial crack, or if power drops suddenly, the machine sends a signal. But that signal must travel through all the layers we described earlier. If it encounters distortion, it might arrive late, incomplete, or unreadable. Operators might see numbers that make no sense and must guess whether the machine is malfunctioning or whether the signal was simply scrambled. Guessing wrong could end the mission. If they assume a scrambled signal is harmless and continue the dive, they risk losing the vehicle. If they assume the worst and abort the mission, they lose precious time at depth. The communication problem is not something that future technology will simply eliminate. Neptune's deepest water does not permit radio waves to travel freely. It does not support lasers across long distances because light scatters almost instantly. It does not allow tetherless broadband systems. No innovation changes the physics of water, pressure, density, or temperature. Engineers can improve acoustic systems, build better signal processing, and design smarter autonomous responses, but they cannot make the trench behave like open air. This limitation shapes the next major obstacle, because the deeper we go into the world of Galathea Deep, the more we encounter not only limits in machines but limits in ourselves. The human body, mind, metabolism, and perception evolved for a world with sunlight, breathable air, and moderate pressure. The trench provides none of these, and even if machines could handle all of the hostile conditions perfectly, humans cannot enter that world without relying entirely on layers of artificial shielding. For all the engineering challenges that stand between us and Galathea Deep, there is another layer of limitation that sits closer to home. It isn't made of metal or electronics. It doesn't crack under pressure or corrode in salt water. It doesn't fall out of calibration or lose power. It's much simpler and far harder to overcome. Even if our machines were perfect, even if they could travel to the bottom of the trench with ease and operate for as long as we needed, there is still the matter of our own bodies. Bodies that evolved in an environment utterly different from the one they would need to enter. No matter how advanced deep-sea technology becomes, we remain creatures built for air, sunlight, and moderate pressure. The trench is not a place we can visit directly without surrounding ourselves in layers of artificial protection. And those layers come with their own limits. When people imagine deep-sea exploration, many picture a diver sinking through blue water in a sleek suit, like something from an adventure film. But even the best diving suits in the world operate at a fraction of the pressures found at the deepest ocean trenches. Traditional scuba divers rarely go past 40 meters without significant risk. Professional divers trained for extreme missions may descend a few hundred meters with specialized gas mixtures. But thousands of meters, no suit, no training, and no human body can approach that without failing instantly. Pressure is the most obvious barrier. Human bodies contain gases in our lungs, in our sinuses, in the spaces between tissues. Under massive pressure, these gases compress. At shallow depths, this can cause discomfort or minor injury. Farther down, it becomes life-threatening. At Hadal depths, it becomes instantly fatal. The pressure at Galathea Deep is more than 1,000 times greater than the pressure at the surface. That force doesn't simply press on the outside of the body. It acts on every molecule, every cell membrane, every gas pocket. Without protection, the body would collapse before a person even realized anything had happened. Specialized atmospheric diving suits can protect divers to a few hundred meters by maintaining internal pressure, but beyond that range, their structure becomes too unwieldy. The materials required to withstand deeper pressures become so thick and heavy that mobility disappears. A suit meant for thousands of meters would need to be a rigid sphere or something close to it, leaving the diver no ability to move arms or legs. At that point, calling it a suit becomes inaccurate. It becomes a small submersible, and the person inside becomes a passenger rather than a diver. Then there's temperature. Even if a theoretical suit could protect against pressure, it would need to handle near-freezing water without letting the diver lose heat. The cold of the trench is relentless. It strips warmth faster than almost any natural environment on Earth. A human placed in that water, even with substantial insulation, would lose body heat faster than they could generate it. Hypothermia wouldn't take minutes. It would take seconds. Any protective system strong enough to resist that heat loss would need its own power source, its own circulation system, and its own thermal regulation, adding even more complexity and weight to an already impossible design. Breathing is another problem. At extreme pressures, normal air becomes toxic. Oxygen becomes poisonous at high partial pressures. Nitrogen becomes narcotic. Helium, often used for deep dives, behaves differently at increased pressure and temperature. Breathing any gas at 1,000 atmospheres becomes pointless because the molecules behave in ways that disrupt neurological function. This is why deep sea vehicles maintain the same internal pressure as the surface. Human physiology depends on stable atmospheric pressure to function predictably. As soon as that stability disappears, so does the body's ability to operate normally. But even if pressure, cold, and breathing could somehow be solved, the environment introduces another barrier: darkness. The human eye is adapted for a world with sunlight. In total darkness, even with artificial lights, vision becomes limited, and the lights themselves create problems. They illuminate only small areas, leaving everything else invisible. For a diver, this lack of context would be disorienting. The brain depends on peripheral cues to maintain balance and orientation. Without them, perception becomes unreliable. Pilots of deep-sea submersibles often report feeling unsure of direction or motion, even inside a stable pressurized cabin. For a person outside, surrounded by moving water and lacking visual reference points, the confusion would be overwhelming. Even the slightest movement could feel exaggerated. A slow current might pull subtly on a diver without them realizing it. A slight change in buoyancy might shift their depth imperceptibly. They wouldn't feel themselves drifting. They wouldn't sense a slope beneath them. They wouldn't see a ridge approaching. They would be enclosed in darkness so absolute they'd lose the ability to gauge distance, direction, or speed. And that's assuming they could move at all. In reality, a pressure-resistant suit heavy enough to survive the trench would likely immobilize the wearer. Moving arms and legs under thousands of atmospheres of pressure, even inside a protective shell, requires mechanisms so strong and so finely engineered that they resemble robotic actuators more than joints. Any movement would be slow, awkward, and energy-intensive. This is why even modern suits capable of descending to moderate depths rely on rigid shells with limited articulation. Another issue rarely discussed is the psychological effect. Humans are not adapted to exist in environments with no sensory cues. At depth, sound becomes muted and strange. Light becomes scarce or absent. Direction becomes ambiguous. The mind, deprived of familiar feedback, begins struggling to interpret anything. People in deep-sea habitats closer to the surface already experience disorientation and stress, even when surrounded by artificial lighting and breathable air. Now imagine being far deeper, encased in a heavy protective shell, with no clear sense of surroundings and no reliable communication. Panic, even in trained individuals, becomes a real possibility, and panic underwater is lethal. All of these limitations make human presence in the trench effectively impossible, without relying completely on a submersible. And once inside a submersible, humans face another set of limitations: space, power, pressure, resistant life support, and navigation demands. Crewed deep-sea vehicles capable of visiting the Hadal Zone are extraordinarily rare. They must be spherical because spheres handle pressure best. They must be built from materials strong enough to resist collapse. They must contain life support systems that maintain breathable air and safe temperature for hours. They must carry batteries or power systems that can handle the long descent, bottom time, and ascent. Every element adds weight. That weight requires more buoyancy. Buoyancy systems add more complexity. The deeper the dive, the more tightly everything must function. Inside these vehicles, the environment is cramped. The pressure outside might be enough to crush metal, but inside everything must remain at 1 atmosphere. Even slight leaks can cause condensation, electrical issues, or air contamination. Divers cannot simply step outside. They must remain inside this small space for the entire mission. That confinement affects planning. A crewed sub cannot carry large sample containers, heavy instruments, or bulky sensors. It cannot maneuver as close to certain structures. It cannot risk areas where sediment might bury it. It cannot linger indefinitely because power is limited. Every minute spent correcting drift or navigating rough terrain reduces the time available for scientific work. And then there is the ascent. Returning from these depths takes hours. Humans cannot simply rise quickly because of risks related to rapid pressure changes inside the vessel's components. Even though the cabin remains at 1 atmosphere, the exterior experiences shifting forces as the vessel rises. The engineering tolerances must accommodate gradual changes. A rapid ascent could induce stresses that machines cannot handle, endangering the crew. This limits emergency responses. If something goes wrong on the seafloor, the sub cannot escape instantly. It must follow a slow, controlled ascent even in urgent situations. Communication further complicates this. As discussed earlier, acoustic messaging is the only reliable method, and it comes with delays. A crew experiencing a mechanical problem must wait for instructions. Those instructions may arrive slowly or incompletely. If the sub must descend, operators on the surface must track it, but sound paths distort with depth. Losing track of a rising crewed submersible, even briefly, creates serious risk because recovery becomes difficult. These limitations mean human exploration of the trench is extremely rare. Most of what we know comes from unmanned vehicles, machines that can risk failure without endangering lives. Humans simply cannot operate directly in Galathea Deep. We can observe, interpret, and theorize from the safety of pressurized capsules or surface vessels, but we cannot exist in that world naturally. Our physiology works in partnership with air pressure, sunlight, temperature, chemistry, and sensory cues that the trench does not provide. Another subtle limitation is the endurance of human concentration. Pilots monitoring a submersible rely on long stretches of intense focus, watching shadowy camera feeds, interpreting sonar, tracking depth changes, and adjusting navigation, all while contending with communication delays, requires mental stamina. Even experienced operators become fatigued, and fatigue increases risk. A misread display or delayed reaction can lead to collision with terrain, entanglement with the tether, or misjudged ascent timing. The trench environment magnifies these hazards. Life support systems impose their own limitations. Oxygen consumption, CO2 buildup, humidity, and internal temperature must remain within safe ranges. These systems take space and power, two resources always in short supply at Hadal depths. Everything inside the crew capsule must remain reliable for hours. Any malfunction becomes dangerous quickly because repairs cannot be made from outside. Even simple issues like condensation forming on instruments can interfere with readings. Humidity must be controlled carefully because electronics inside a sealed environment generate heat. Cooling systems must operate without introducing droplets or fog. Despite these challenges, humans continue sending machines into Galathea Deep because curiosity outweighs difficulty. But the reality remains that we cannot enter the trenches ourselves. We cannot swim through them. We cannot walk along the sea floor. We cannot navigate the unseen slopes or feel the currents on our skin. Every sensation we experience there must be filtered through a machine. Every discovery is at a distance. This is not a failure of imagination or engineering. It is simply a matter of biology. The trench is a world shaped by pressure, cold, and darkness, conditions stable and absolute. Our bodies evolved for environments that change over hours, not millions of years. The trench does not adapt to us. We must adapt to it through tools, and those tools come with limits we cannot escape. As we reach toward the end of this journey, there is one final truth to consider. For all the obstacles, all the dangers, all the layers of resistance, there is a deeper reason Galathea Deep remains out of reach, one that has nothing to do with machinery or biology. Some places on Earth remain mysterious, not because we cannot get there, but because the environment itself restricts what can be known. At the very bottom of the deepest ocean, the world hides more than it reveals. When people talk about Earth's unexplored places, their minds often jump to distant planets, hidden forests or remote deserts. But the most unexplored place of all is much closer than any of those. It lies beneath us, below the waves, below the visible world, below the parts of the ocean that fishing boats skim across and research ships measure. It sits in darkness so complete that no sunbeam has ever touched it, in silence shaped by pressure that bends metal, in cold older than the first creatures that swam the surface. And even though we have visited it with machines, even though we have maps and data and grainy footage, Galathea Deep remains one of Earth's least understood environments. Not because nobody has tried to study it, but because everything about it narrows what is possible to learn. The idea of an unexplored place often creates an image of something hidden behind a barrier, a cave, a jungle, a remote mountain range. But the trench is not hidden behind a door we need to unlock. It's open water, accessible in principle to any vessel that can travel offshore. The real barrier is that reaching the bottom doesn't mean seeing the whole environment. It means seeing a tiny circle of light surrounded by blackness, layered water, drifting sediment, and pressures that threaten to collapse anything we use to explore it. Even when a submersible makes it all the way down, what it can observe is only a small fraction of what exists there. A few meters of sea floor, a handful of organisms, an isolated slope or ridge, and then time runs out. The machines need to return to the surface long before they've revealed much. That's part of why the trench remains one of the last untold stories on Earth. Every visit is brief, every moment is fragile, every observation depends on machines functioning perfectly in a place where machines rarely perform smoothly. Most environments we explore allow repeat visits with some consistency. Mountain peaks don't change drastically from month to month. Forests shift slowly over decades. Even deserts, despite their harshness, permit extended, detailed study. But the deep sea doesn't. The barriers we've talked about — pressure, cold, darkness, layered water, communication distortions, moving sea floor — combine into a limit on how often we can observe and how much we can learn during each observation. This creates a strange kind of knowledge gap. We know the trench exists, we know its approximate depth, we know some of its geology and chemistry, we've seen a handful of the organisms that live there, but we haven't watched how those organisms behave over time. We haven't followed their life cycles, we haven't studied how they interact, we haven't mapped the entire terrain with detail comparable to what we have for mountain ranges or river systems. We don't know which species live exclusively in one corner of the trench and which travel across larger sections. We don't know how often landslides reshape certain slopes. We don't know whether there are features we have never approached simply because our machines always landed in the same narrow areas. Every dive reveals something, but every dive reveals only something small. Even the simple act of measuring the trench's depth has changed over time. Early measurements suggested one value. Later measurements suggested another. Modern mapping provides a more accurate range, but even now tiny variations remain because sediment shifts, instruments behave unpredictably under pressure, and the trench itself moves subtly over decades due to tectonic activity. It is not a static place we have fully charted. It is a moving system we glimpse occasionally. What makes the trench particularly mysterious is that everything happens slowly enough that human observation, measured in hours per expedition, barely scratches the surface. A community of organisms might only interact visibly once every few days. A chemical exchange might occur steadily over years. Sediment accumulation might unfold over centuries. We send machines that stay for a fraction of a day and expect to understand entire ecosystems built around a different sense of time. Imagine trying to understand a forest by visiting it for 10 minutes once every few years, only at night, only with a flashlight that illuminates a small patch of ground, and only while standing inside a small protective booth that cannot move easily. That is what we do in the trench. It isn't for a lack of effort. It's because the conditions physically restrict us to brief, narrow views. And even during those brief views, the environment resists interpretation. Shadows behave unpredictably because the water absorbs light differently at depth. Cameras struggle to capture motion clearly because particles drift constantly. Biological behavior becomes hard to interpret when creatures are adapted for dark, slow habitats. A species might appear motionless in footage not because it is inactive, but because its movements are too faint or too gradual for our limited observation windows. We might assume a region is barren based on a short visit when, in reality, life thrives there on a timescale that doesn't match our instruments. Then comes the problem of returning samples to the surface. Many organisms from Hadal depths cannot survive the ascent. Their bodies collapse or their chemistry changes long before they reach daylight. This leaves researchers studying fragments or altered versions of what originally existed. We do not get to examine these creatures in their natural state. We analyze what remains after the environment has already been stripped away. It's like trying to understand a snowflake after carrying it into a warm room. Even geological samples behave differently once removed from the trench. Pressures shift, temperatures rise, chemical reactions occur that would never happen at depth. Instruments that measure sediment composition must account for these changes. But even with careful handling, some information is always lost. This is why many aspects of the deep remain hypotheses rather than confirmed facts. We infer based on the data we can gather, but inference is not the same as direct observation, and the trench rarely offers the clarity needed to turn inference into certainty. Another part of the reason the deep remains an untold story is simply the scale. The Hadal Zone is scattered across trenches around the world. Each trench has its own shape, chemistry, and geological forces. They aren't identical environments repeated in different locations. They are unique worlds separated by thousands of kilometers of ocean. Galathea Deep is one of these worlds. The Mariana Trench holds another, Tonga another, Japan another. If each one requires machines built specifically to handle its conditions, then exploring them all becomes a monumental undertaking. Unlike mountain peaks, which can be surveyed by aircraft and satellites, trenches demand physical descent every time we want details. There is no shortcut. Funding also shapes what we know. Deep-sea missions are expensive. They require specialized ships, expert teams, high-tech materials and long travel times, and they involve high risk. Losing a multi-million-dollar vehicle is always a possibility. Each mission demands careful planning. Missions cannot happen every month. They occur when resources, weather and technology align. This means years may pass between dives to the same region. A world that changes slowly becomes even harder to understand when the intervals between observations stretch so long that comparisons become difficult. This scarcity of visits creates gaps in understanding. If a species appears on one dive and not on the next, does that mean it moved, hid, died out, or simply avoided the small patch of seafloor illuminated by the submersible's lights? The lack of continuous observation keeps most questions unanswered. In some ways, the trench remains untold because we are used to environments revealing themselves when approached. Stand on a hilltop and you see the valley below. Dive near a coral reef and the entire ecosystem bursts into view. Enter a cave with a bright lamp and the walls reflect back the story of their formation. The deep ocean does not respond this way. It shows nothing unless forced. It reveals only what we shine light on, and even then the light shows only what happens in that thin temporary circle. Some people assume that technological advancement will eventually remove these limits. Better materials, stronger submersibles, faster communication systems, more autonomous vehicles. There's truth in that. We will almost certainly build machines that operate longer at depth, handle more pressure, maintain heat better, and see farther through dark water. But no matter how advanced these machines become, the environment itself imposes boundaries. Pressure will always compress, cold will always slow chemical reactions, darkness will always absorb light, layered water will always bend sound, and sediment will always obscure vision when disturbed. We can work around these factors, but we cannot remove them. They are part of the trench, and they shape how knowledge is gathered there. This isn't a barrier in the negative sense. It's simply the nature of a world that formed far beyond human scales. The deep did not evolve for us, and we cannot redesign it to fit our needs. Instead, we study it in small steps, glimpses collected over decades, pieces of information that slowly assemble into something resembling understanding. But even as new discoveries appear, the trench retains its character. A place where secrets outnumber answers. A place where every mission raises more questions than it resolves. A place where certainty remains rare because the environment gives so little away. And strangely, this is part of why the trench captures imagination. For all our advances, for all our satellites, supercomputers, telescopes, and laboratories, there remains a place on Earth where mystery survives. Not because we lack curiosity, not because we lack ability, but because the environment itself demands patience, precision, and humility. Galathea Deep won't give up its story easily. It doesn't resist out of hostility. It simply exists in a form that doesn't translate quickly into human understanding. We approach it with lights and sensors and pressure-resistant hulls, and it responds with silence. We return with a few images, a few samples, some questions answered, Many more opened, and then the trench returns to its dark stillness, as if nothing had happened. There's something grounding in that. A reminder that Earth still holds places beyond our full reach. A reminder that mystery is not a relic of the past. A reminder that some stories unfold slowly because the world itself moves slowly. And one day, with patience and better tools, we'll gather more pieces, not all of them, not enough to claim total understanding, but enough to expand the circle of light slightly farther into the dark.